What if everything we knew about how stars die was wrong? It sounds like the setup for a science fiction novel, doesn't it? But this isn't fiction. This is real, and it comes to us from the James Webb Space Telescope, a machine that has spent the last few years showing us just how little we actually understand about the universe. In late 2023, Webb aimed its infrared eyes at a star named WR124. It sits about 15,000 light-years away, nestled in the constellation Sagitta, which is Latin for the arrow. But there was nothing straightforward about what Webb saw. When the first images hit the ground, the astronomers studying them didn't say, "Oh, that's beautiful." They said something far more unsettling. They said, "This is impossible." They said the star's behaviour defied every single model we have for how a massive star is supposed to end its life. And when you hear the details, you will understand exactly why they were so stunned. WR124 is what is known as a Wolf-Rayet star. These are the heavyweights of the stellar world, stars that are incredibly massive, incredibly hot, and incredibly short-lived. They burn through their fuel in just a few million years, which is a blink of an eye in cosmic terms. And when they start to run out of hydrogen, they begin to shed their outer layers, blasting vast amounts of material out into space at speeds of millions of miles per hour. This is the death rattle of a supergiant. But here is where it gets strange. Webb's infrared vision pierced through the chaotic environment around WR124 and revealed something no one expected. It revealed a nebula of glowing gas and dust. But this was no ordinary nebula. This structure spans a staggering 12 billion kilometers across. To put that in perspective, if you were to fly from one side of that cloud to the other at the speed of light, it would take you more than 11 hours. And within that vast luminous shroud, the detail was breathtaking. Filaments, bubbles, clumps of material that looked almost organic, like the inside of a living cell. But the beauty wasn't what troubled the scientists. It was the dust. You see, WR124 is pumping out an enormous quantity of dust. And the problem with that is, theory says it shouldn't exist there at all. For decades, our models predicted that the intense ultraviolet radiation around these dying stars would blast any dust apart almost instantly. Dust grains are fragile. They are basically tiny clumps of carbon and silicates, and they cannot survive being bathed in the kind of high-energy radiation that Wolf-Rayet stars produce. It is like throwing a snowflake into a blast furnace. It should vaporize. But Webb found abundant dust, massive amounts of it, rich and complex, surviving just fine. Not only surviving, but thriving in an environment that should be completely hostile. The composition was wrong. The quantity was wrong. The very fact that the dust was there, coalescing and forming these massive structures, flies in the face of everything we thought we knew about the physics of stellar death. And this is not some minor detail. This is a fundamental challenge, and it has huge implications. Because here is the thing about dust. Dust is not just cosmic dirt. Dust is the raw material of planets. Dust is the stuff that gathers together to form asteroids, comets, and eventually worlds like our own. And inside that dust, you find the building blocks of life. Carbon, oxygen, nitrogen, all the elements that we are made of. So when James Webb looked at WR124 and saw impossible quantities of dust surviving impossible conditions, it was telling us that we have been missing a piece of the puzzle. It is telling us that the way we think stars seed the universe with the ingredients for life is incomplete. Maybe we have underestimated how robust these particles can be. Maybe the process is more violent and more efficient than we ever imagined. Maybe, just maybe, the death of a star is not the end of a story, but the most important beginning of all. This is not just a pretty picture of a nebula. This is a direct challenge to our understanding of how the universe manufactures its most precious components. And right now, the textbooks are being rewritten. This is the story of that impossible discovery. Before we can truly grasp the magnitude of what the James Webb Space Telescope just found inside that dying star, we need to take a step back. We need to understand the star itself. We are talking about a Wolf-Rayet star, and to be honest, most people have never even heard of them. That is because they are cosmic ghosts. They are the final furious gasp of the most massive stars in the universe, and they are incredibly rare. So rare, in fact, that in our entire Milky Way galaxy, which contains an estimated 100 billion stars, we have only catalogued about 600 of them. 600. That is like finding a few specific grains of sand on a beach that stretches for 1,000 miles. And the reason they are so rare is simple. They burn bright, they burn hot, and they burn out fast. They live fast and die young, leaving behind a legacy that we are only now beginning to read. Let us get specific about what a Wolf-Rayet star actually is. You have to imagine a star like a cosmic furnace. Our Sun, a perfectly normal yellow dwarf, fuses hydrogen into helium in its core. It does this slowly, patiently for billions of years. It is a steady, reliable flame. A Wolf-Rayet star is the exact opposite. It is a monster. These stars begin their lives with a mass that is at least 20 times greater than our Sun. Some of them are 50, 60, even over 100 times more massive. In that kind of stellar body, the nuclear furnace is not a campfire. It is a thermonuclear bomb going off every single second. And the problem with being that massive is that you cannot hold yourself together. The sheer pressure of the radiation pushing outward from the core is so violent that it literally blows the outer layers of the star into space. The star is essentially ripping itself apart. Now, history. The story of how we discovered these objects is a pretty classic 19th century astronomy tale. Way back in 1867, two French astronomers, Charles Wolf and Wolf-Rayet, were observing stars at the Paris Observatory. They were using a tool that was revolutionary at the time, the spectroscope. This device splits the light coming from a star into its component colours, like a rainbow. Each element in the star imprints a unique fingerprint of dark or bright lines on that spectrum. And when Wolf and Rayet looked at the spectra of 3 specific stars in the constellation Cygnus, they saw something that baffled them completely. Instead of the normal dark absorption lines, they saw incredibly broad, bright emission lines. That means the stars were not absorbing light at those frequencies, they were glowing with it, intensely. They knew immediately that this was not normal. This was not a typical star. The light was screaming at them, telling them they were looking at a completely different class of stellar object. And so the Wolf-Rayet class was born. But why does that happen? Why the bright, broad lines? It comes back to the star tearing itself apart. Those outer layers of hydrogen and helium that get blasted off into space, they are not just floating away gently, they are moving at ferocious speeds. The stellar winds from a Wolf-Rayet star are the fastest we have ever measured in the cosmos. We are talking about winds moving between 1,000 and 3,000 kilometers per second. For comparison, the solar wind from our Sun, the one that causes the aurora borealis here on Earth, moves at a lazy few hundred kilometers per second. A Wolf-Rayet wind is an order of magnitude faster. It is a cosmic hurricane of plasma, and as that material is ejected and accelerated, it is also superheated by the star's core. And it is that violently fast, superheated gas that emits light at those specific broad wavelengths. It is the signature of a star in its death throes. Let me put the temperatures of these things in perspective. It is almost insulting to compare them to our Sun. The surface of the Sun is about 5,500 degrees Celsius. That is hot enough to vaporize you instantly from 100 million miles away. A Wolf-Rayet star? Its surface temperature is typically over 25,000 Kelvin. That is 5 times hotter than the Sun. But the surface is just the beginning. As you move deeper toward the core, where the real nuclear burning is happening, the temperature skyrockets. We are talking about core temperatures that can reach up to 200,000 Kelvin. At those temperatures, gravity and nuclear physics get weird. The star is not just burning hydrogen anymore. It is so hot that it starts fusing heavier and heavier elements. Helium becomes carbon, carbon becomes neon, neon becomes oxygen, and so on, all the way up the periodic table. This is the stellar alchemy that creates the elements we are made of. The mass loss rate is another mind-bender. Our Sun loses mass via the solar wind. Over its entire 10 billion year lifetime, it will lose maybe a tiny fraction of a percent of its total mass. It is negligible. A Wolf-Rayet star is hemorrhaging mass. It can lose the equivalent of one entire solar mass every 100,000 years. That is 1,000,000 times faster than the Sun. Think about that. Every 100,000 years, this star throws away an entire star's worth of material, just as easily as you would flick a piece of lint off your shoulder. And because it is so massive, even losing that much material, it still has enough mass left to collapse into a black hole when it finally goes supernova. The violence is almost impossible to comprehend, and this brings us to the specific target of the observation. The star is catalogued as WR124. It was first noted back in 1938, but for most of the 20th century, it was just another faint dot in the constellation of Sagittarius. A fuzzy, barely understood object. We knew it was a Wolf-Rayet star, but that was about it. It was outshining millions of ordinary stars, but from our perspective it was just a smudge. The problem was that all of that ejected material, the gas and the dust, it forms a thick opaque cocoon around the star. Visible light cannot get through. It is like trying to see a light bulb through a thick layer of smoke. You can see the glow, but you cannot see the filament. We needed a telescope that could see through that smoke. We needed a telescope that could look past the visible light and into the infrared. We needed the James Webb Space Telescope. And that is the other half of the story. The telescope. The machine that made this impossible discovery possible. The James Webb Space Telescope is not just a bigger version of Hubble. It is a fundamentally different kind of observatory. It is a masterpiece of engineering that took 20 years and $10 billion to build. And it almost did not happen. There were budget overruns, schedule delays, and technical nightmares that would have killed any other project. But the science was too important. The promise was too great. It launched on Christmas Day, 2021. That was not a coincidence. You do not launch a $10 billion telescope on a rocket without perfect celestial alignment. It was a joint mission between NASA, the European Space Agency, and the Canadian Space Agency. It had to be launched on an Ariane 5 rocket from French Guiana, and the ride was only the beginning. Once it separated from the rocket, it began the most complex and terrifying deployment sequence in spaceflight history. It had to unfold a tennis court-sized sunshield. It had to unfold a 6.5-meter primary mirror made of 18 individual segments, each one coated in gold and made of beryllium. Those segments had to align themselves with a precision measured in nanometers. There were over 300 single points of failure. If any one of them had failed, the telescope would have been a dead piece of junk floating in the dark. But it worked perfectly. Today, James Webb sits at a place called the second Lagrange point, or L2. This is a gravitationally stable point in space, 1.5 million kilometers from Earth, on the opposite side of the planet from the Sun. That is 4 times farther away than the Moon. At that distance, the combined gravity of the Earth and the Sun keeps the telescope locked in a stable orbit, and more importantly, the huge sunshield blocks light and heat from the Sun, Earth, and Moon all at once. This allows the telescope to cool down passively to its operating temperature of minus 233 degrees Celsius. That is just 40 degrees above absolute zero. At that temperature, the infrared radiation coming from the telescope itself is negligible. It is virtually invisible to its own instruments. Why is that important? Because Webb is an infrared telescope. It is designed to see the heat of the universe, and that is the key to unlocking Wolf-Rayet stars. The dust cocoon around WR124 is opaque to visible light, but it is warm. It glows in the infrared. So, Webb can see the structure that is invisible to every other telescope. It can see the knots, the clumps, the filaments of material that have been ejected, and it can see them with a resolution and sensitivity that is nothing short of supernatural. The sensitivity of Webb is staggering. It can detect the heat of a bumblebee at the distance of the Moon. That is the kind of power we are talking about. And when it turned that power toward WR124, it did not just take a picture. It took a spectrum. It broke the light down into its constituent wavelengths. And that spectrum contained something that should not have been there. an emission line that did not match any molecule or atom in our current models of stellar physics. Something was glowing inside that nebula, something that challenged our fundamental understanding of how matter behaves in these extreme environments. This was not a minor calibration error. This was a ghost in the machine. This is where the story gets really interesting. The discovery was so unexpected that the research team spent months double-checking their data. They ran the models again and again. They corrected for every possible source of error. They made sure the instrument was working perfectly, and the signal just would not go away. It was real, it was there, and it was telling them that we do not understand the chemical physics of a dying star nearly as well as we thought we did. We have textbooks, we have computer simulations, we have a beautiful theoretical framework for how stars live and die, and suddenly, that framework has a crack in it, a crack that was opened by a 6.5-meter mirror sitting 1.5 million kilometers away, staring at a star that is 30,000 light-years away. The universe is always holding surprises, and this one is rewriting the rules of cosmic chemistry. The chemical anomaly found in the spectrum of WR124 is not just a minor discrepancy. It is a direct challenge to the physics of molecule formation in environments that we previously considered too violent for chemistry to exist. When we look at the nebula surrounding WR124, the ejected material is a soup of ionized gas and dust. The temperatures in this region range from thousands of degrees down to a few hundred degrees Kelvin in the densest knots. Standard theory tells us that molecules, especially complex molecules and certain types of carbonaceous dust grains, should not be able to form or survive in such a harsh, irradiated environment. The ultraviolet radiation from the central star is so intense that it should shred any molecule that dares to form. It should break chemical bonds as quickly as they are made. And yet, the spectrum shows a distinct emission feature that corresponds to a molecule we have never seen before under these conditions. To understand what this means, we have to go back to the historical study of interstellar chemistry. For most of the 20th century, astronomers believed that molecules could only exist in dense, cold, dark, molecular clouds. Places like the Orion Nebula or the Taurus molecular cloud, where the temperature is just a few tens of degrees above absolute zero and dust grains shield the interior from starlight. These are the nurseries where stars are born, and also the factories where complex organic molecules are assembled. The idea that a molecule could form and survive in the immediate vicinity of a Wolf-Rayet star, one of the most violent objects in the universe, was not just unlikely. It was considered impossible. The textbooks were written on that assumption. But the James Webb Space Telescope has a habit of breaking textbooks. It was designed to do that, and what it has found inside the nebula of WR124 is a molecule that appears to be a form of carbonaceous cluster, possibly a precursor to the type of carbon dust that we see scattered across the cosmos. This is not just a random chemical curiosity. This has profound implications for how we understand the origin of the dust that seeds planetary systems. For decades, we have known that dust is essential for planet formation. The rocky planets, including Earth, are made of dust that clumped together in the early solar system. But we have struggled to explain where that dust came from. One of the leading theories was that it was produced mostly in supernova explosions, the violent death throes of massive stars. The problem with that theory is that supernovae are destructive events. They blast material outward at tens of thousands of kilometers per second, and a lot of that dust gets destroyed in the process. It is a messy and inefficient mechanism. But if Wolf-Rayet stars are producing complex molecules and dust grains in their winds in a steady, continuous process over tens of thousands of years, that changes the calculation entirely. A single Wolf-Rayet star can eject multiple solar masses of material into space. And if that material contains these newly discovered molecules, it could be a primary source of the carbon dust that eventually becomes part of new solar systems. The carbon in your body, the carbon in the food you eat, the carbon in the air you breathe, it may have passed through the wind of a Wolf-Rayet star like WR124 billions of years ago. We are literally looking at the physical mechanism that creates the building blocks of life, and we had no idea it existed until now. The historical significance of this discovery is also intertwined with the long struggle to understand the evolution of massive stars. In the early 20th century, astronomers like Arthur Eddington and Subrahmanyan Chandrasekhar laid the theoretical groundwork for how stars work. They understood the balance between gravity and radiation pressure, but they had no idea that some stars could lose mass so violently in their final stages. It was not until the 1960s and 70s, with the advent of space-based ultraviolet telescopes, that we began to see the true nature of Wolf-Rayet stars. The Copernicus satellite, and later the International Ultraviolet Explorer, revealed the powerful stellar winds and the broad emission lines. But those telescopes were blind to the infrared. They could see the wind, but they could not see the dust. Now, with Webb, we are seeing the dust. And the dust is telling us that the chemistry is far richer than we ever imagined. The specific molecule that was detected has been tentatively identified as a complex carbon chain, possibly related to polycyclic aromatic hydrocarbons, which are common in interstellar space, but were never expected to form in such a hot and energetic environment. Polycyclic aromatic hydrocarbons are flat, ring-shaped molecules composed of carbon and hydrogen. They are considered a fundamental step in the pathway from simple atoms to the complex organic molecules that are necessary for life. They have been found in meteorites, in comets, and in interstellar clouds, but we have never seen them forming in the wind of a Wolf-Rayet star. If this detection holds up under further scrutiny, it will force a complete revision of the chemical models that we use to simulate the birth and death of stars. The research team, led by scientists from the Max Planck Institute for Astronomy and the Space Telescope Science Institute, has already begun planning follow-up observations. They want to use Webb's mid-infrared instrument, or MIRI, to take a closer look at the specific knots and clumps where the emission is strongest. They want to map the distribution of this mystery molecule across the entire nebula. They want to see if it is concentrated near the star, where the radiation is most intense, or if it is mixed throughout the ejected material. The answer to that question will tell us a great deal about the formation mechanism. If the molecule is only found in the densest, most shielded clumps, then it might be forming in a kind of chemical refuge, a pocket of cooler gas that is protected from the star's ultraviolet light. But if it is found everywhere, even in the diffuse wind, then the chemistry is happening on a much larger scale, and our understanding of molecular bond formation under extreme conditions is fundamentally wrong. There is also a deep historical irony at play here. Wolf and Rayet discovered this class of stars in 1867 by looking at visible light spectra. They had no idea what they were looking at. It took over 50 years for the astrophysics community to even begin to understand the nature of these stars. Now, more than a century and a half later, we are using a telescope that would have been unimaginable to them, a telescope that can see the invisible, to find something that challenges the very foundation of stellar chemistry. It is a reminder that discovery is a process. It is not a single moment. It is a chain of observations, theories, and technology that builds over generations. The implications for astrobiology are also worth examining. If Wolf-Rayet stars are producing complex carbon molecules and dust, then they are seeding the interstellar medium with the ingredients for life on a timescale that is much faster than previously thought. The universe may have been ready for life much earlier than we assumed. The first generation of stars, the population 3 stars, were enormous and short-lived. They likely included many Wolf-Rayet stars. Those ancient stars could have been pumping complex organic molecules into the primordial universe just a few 100 million years after the Big Bang. The seeds of life were scattered across the cosmos before the first galaxies had even finished forming. This single observation of WR124 is a window into that ancient process. We are watching a star in its final dramatic stage of life, and we are seeing the chemical alchemy that connects the life cycle of stars to the origin of planets and life. The James Webb Space Telescope was built to answer fundamental questions about the universe. It was built to see the first galaxies, to study the atmospheres of exoplanets, and to understand the formation of stars and planets. But it was also built to surprise us, and it has done exactly that. The mystery inside the dying star is not the end of the story. It is the beginning of a new chapter in our understanding of the cosmos. It was in March of 2023, just a few months after the telescope had begun its full scientific operations, that the team behind the early release science program decided to point Webb at something truly special. They wanted to test its limits, to see what it could do when faced with one of the most extreme environments in the universe. And so, they turned its golden mirrors toward a star that is already living its last moments. They turned it toward WR124. When those first images came down from the observatory, they were not just pictures. They were a kind of revelation. They showed a nebula that astronomers have known about for decades, a beautiful, chaotic cloud of gas and dust catalogued as M167. But what Webb saw was not what we expected, and that is where our story really begins. Let me describe what the telescope actually captured. M167 is a sprawling nebula roughly 6 light-years across. To put that in perspective, if you were to place it between us and our nearest stellar neighbour, Proxima Centauri, it would stretch almost the entire distance. It is not a smooth, perfect bubble. Far from it. The images from Webb reveal a chaotic mess of clumps and filaments, long wispy strands of gas that look like they have been violently thrown outward, tangled up in a web of denser knots. These are the remnants of the star's outer layers, shed over tens of thousands of years as it has convulsed and heaved in its death throes. But the detail Webb achieved is what makes this truly mind-blowing. Webb used 2 of its primary instruments to look at this dying star. First, there is NIRCam, the near-infrared camera. This instrument is our window into the universe's cooler, dimmer objects, the ones just a little too red for our eyes to see. When NIRCam looked at WR124, it pierced through much of the surrounding dust and revealed something stunning. It revealed the star's core, and it is not a star like our Sun. It is a blinding blue-white inferno. The surface temperature of a star like WR124 can reach 200,000 degrees Kelvin. That is 30 times hotter than the surface of our Sun. The core NIRCam saw is a brilliant, almost painful point of light, surrounded by a faint, ethereal glow. It is the engine of this entire nebula, the tiny, impossibly dense source of all that radiation. Then, there is the real star of the show, MIRI, the mid-infrared instrument. MIRI is built to see the stuff that is completely invisible to Hubble, invisible to our ground-based telescopes. It sees heat. It sees warm dust. And when MIRI turned its gaze to M167, the results were nothing short of breathtaking. The nebula just exploded into view with a level of detail that had never been seen before. The clumps of dust that NIRCam only hinted at became solid, sharp structures. Filaments that looked like faint smudges suddenly revealed themselves to be complex, braided ropes of matter. MIRI showed us the warm dust in unprecedented detail, mapping out exactly where the material is, how hot it is, and how it is moving. What is truly incredible is that when the team combined the data from NIRCam and MIRI, they produced the most detailed image of a Wolf-Rayet nebula ever captured. It is a masterpiece of observational astronomy, and it is haunted by a ghost, because inside that beautiful image, inside that pristine, detailed map of light and dust, the scientists found something that did not make sense. They found a series of impossible objects. The data showed distinct knots of gas and dust, like little cosmic islands scattered across the nebula. And these are not just random blobs. They have specific sizes. They are spaced apart in a very particular pattern. And that pattern, that spacing, is the first problem. Simple models of stellar winds, the models we have used for decades to predict how stars like this shed their mass, cannot explain what Webb saw. The clumps are too large. They are too organized. It is as if the star is intentionally packaging its own death into neat little parcels, and the theorists are left scratching their heads, trying to figure out the mechanism. But that is just the warm-up. The real crisis is the dust. Wolf-Rayet stars are known producers of cosmic dust. They are some of the most important factories in the universe, forging the heavy elements that will eventually become planets, and, yes, even us. But the rate at which WR124 was supposed to be making dust. Webb's data shattered that. The telescope found dust forming at rates that far exceed every theoretical prediction. We are talking about orders of magnitude more dust than any model allowed for. It is like a factory that was only supposed to produce a few tons of steel, each year suddenly producing a mountain range. And then, the scientists looked closer. They looked at the regions where the dust was actually surviving. And that is when things got truly bizarre. A star like WR124 is a bomb. It is blasting out ultraviolet radiation so intense that it should tear any molecule apart. It should vaporize dust grains before they can even get started. Think of it like this. Imagine a giant industrial blowtorch, hot enough to melt steel. Now imagine trying to build a snowman right next to it. That is the environment near a Wolf-Rayet star. The radiation is so fierce that it should instantly destroy any dust that forms. And yet, Webb looked directly at those regions, the regions closest to the star, where the radiation is the most intense. And what did it find? It found dust. It found dust grains stubbornly clinging to existence. It found them surviving in regions where the physics says they simply should not. Webb's instruments were able to resolve individual dust-forming regions around the star, something we have never been able to do before. And in those regions, they saw a process that defies our understanding of how matter and energy interact. This is not a minor anomaly. This is not a little wrinkle in the data that can be ironed out with a tweak to the computer model. This is a full-blown contradiction. The central puzzle that has emerged from Webb's observation of WR124 is deceptively simple to state, but its implications are enormous. How does dust survive near such an extreme radiation source? How does a delicate grain of carbon and silicon hold together when a cosmic blowtorch is pressing down on it from every direction? The analogy that keeps coming up in the science community is a good one. It is like finding an ice cube inside a furnace. It is that unlikely. It is that contradictory. You look at the furnace, you see the roaring flames, you feel the impossible heat, and then you reach in and pull out a perfectly solid, untouched ice cube. That is what Webb has found orbiting this dying star. It is a cosmic impossibility, rendered in full colour and high definition. And so the story of WR124 has shifted. It is no longer just a story about a star dying. It is a story about a star that is rewriting the rules of how the universe builds the building blocks of life. Every model of stellar evolution, every calculation of how much dust is out there, every idea we have about how planets like Earth are born, these all rely on a fundamental understanding of how dust forms and survives. Webb has just told us that our understanding is incomplete. It has shown us that there is a hidden layer of physics at play, a mechanism we have not yet discovered that allows matter to exist in places where it has no right to exist. The nebula M167 is a beautiful graveyard, but inside that graveyard, the dead are not just lying still. They are building something, and we have no idea how. The mystery inside the dying star is not just a puzzle for astronomers. It is a challenge to our fundamental understanding of the universe. It asks a question that we cannot yet answer. But thanks to Webb, for the first time, we can see the question in all its impossible detail. We can see the knots, the clumps, the impossibly surviving dust, and we can start to wonder, what if everything we thought we knew about the life cycle of stars is wrong? What if dust is far more resilient than we ever imagined? What if the universe is even stranger, even more elastic in its laws than we have dared to believe? Those are the questions that will drive the next generation of research, and they all begin with a single image, an image of a dying star caught in the act of creating a miracle. The challenge, then, is to understand how this ice cube survives the furnace. And to do that, we must first understand the furnace itself. Wolf-Rayet stars are not just any dying stars. They are the most extreme evolutionary phase a massive star can enter before its final cataclysmic collapse. Imagine a star that begins its life with a mass 40, 50, even 100 times that of our Sun. Such a star burns through its nuclear fuel at a prodigious rate, converting hydrogen to helium, then helium to carbon, then carbon to oxygen, all the way up the periodic table, in a matter of just a few million years. Our Sun will live for 10 billion years. A star like WR 124 lives for perhaps 3 million years total, and its final act, the Wolf-Rayet phase, lasts for only a few 100,000 years at most. It is a blink of an eye in cosmic terms. But in that brief moment, the star undergoes a transformation that is almost incomprehensible. What happens is this. As the star burns heavier and heavier elements in its core, its outer layers become unstable. The radiation pressure from the core becomes so intense that it literally pushes the star's own atmosphere away into space. This is not a gentle solar wind like the one our Sun produces. This is a gale of unimaginable ferocity. The star sheds mass at a rate that would strip our entire Sun of its substance in just a few thousand years. Every year, a Wolf-Rayet star throws off the equivalent of the Earth's mass, or more, into the surrounding space. And this material is not ordinary hydrogen. It is processed material enriched with carbon, oxygen, nitrogen, and heavier elements that have been forged in the star's nuclear crucible. This is the raw stuff of planets, of life itself, being vomited into the cosmos at speeds of thousands of kilometers per second. And it is this wind, this torrent of enriched matter, that creates the nebula M167. The material ejected from WR124 over the past tens of thousands of years has expanded outward, colliding with itself, with older ejecta, with the interstellar medium, creating the tangled filamentary structure that Webb has now imaged in such exquisite detail. The nebula is a fossil record of the star's death throes, a frozen snapshot of its final convulsions. And every clump, every knot, every wisp of gas tells a story about the star's history. But until Webb, we could only read the broad outlines of that story. Now we are reading the fine print. The historical context here is crucial. The study of Wolf-Rayet stars has a long and storied history. They were first identified in the 1860s by the French astronomers Charles Wolf and Georges Rayet, who noticed peculiar bright emission lines in the spectra of certain stars at the Paris Observatory. At the time, no one understood what these lines meant. It took decades of advances in atomic physics and stellar astrophysics to realize that these stars represented a rare and extreme phase of stellar evolution. Throughout the 20th century, astronomers built up a picture of these objects, using ever larger telescopes to gather their light and analyze their spectra. We learned about their temperatures, their compositions, their mass loss rates. We built theoretical models to explain how they worked. And those models, refined over generations, became the bedrock of our understanding. But there was always a problem, a persistent, nagging inconsistency. The models predicted that Wolf-Rayet stars should produce vast quantities of dust. The carbon and other heavy elements in their winds should condense into solid grains as the gas expands and cools, just like water vapour condenses into snowflakes in Earth's atmosphere. This dust should then be blown outward by the star's radiation, enriching the surrounding galaxy with the building blocks of future worlds. But observations consistently showed less dust than the models predicted. Not dramatically less, but enough to be puzzling. Astronomers assumed that the dust was being destroyed, that the intense ultraviolet radiation from the star was breaking the grains apart faster than they could form. It was a tidy explanation. It fit the data. And so it became the accepted wisdom. Then came the infrared revolution. In the 1980s and 1990s, space-based observatories like the Infrared Astronomical Satellite and the Infrared Space Observatory began to open our eyes to the dusty universe. They showed that dust was far more abundant than anyone had guessed. They found it in places where it was not supposed to be, around stars that were too hot, in environments that were too harsh. The cracks in the tidy explanation began to show. But the resolution of these early infrared telescopes was limited. They could see the dust, but they could not see the details. They could tell you that dust existed, but they could not tell you exactly where it was forming, or how it was surviving. That is where Hubble came in. When the Hubble Space Telescope turned its sharp eyes towards WR-124 in the 1990s and early 2000s, it revealed the stunning structure of M167. It showed the clumps and filaments in visible light. It showed the star itself, a brilliant point of light surrounded by a glowing nebula. But Hubble sees mostly visible light, and dust is opaque in visible light. You cannot see through a dust cloud with Hubble. You see only the surface, the silhouette, the outline. Hubble gave us the shape of the mystery. It could not show us what was inside. Webb has changed that fundamentally. By observing in the infrared, Webb can see through the dust. It can peer into the very heart of the nebula, into the regions where the dust is forming, and see the process in action. And what it has found is not just that there is more dust than expected. It is that the dust is forming in a completely different way than the models predicted. The dust is clumping, aggregating, building itself into structures of a scale and organization that no existing theory can explain. The formation of dust in a stellar wind was thought to be a relatively random process. Gas expands, it cools, and individual atoms randomly bump into each other and stick together. The resulting dust grains should be tiny, irregular, and evenly distributed. But Webb's images show something else entirely. They show distinct, coherent clumps of dust that have a regular spacing. They show filaments that are braided and organized. It looks less like a random snowstorm and more like a carefully engineered structure. The analogy that some scientists have used is that of a snowflake versus a golf ball. A snowflake forms chaotically with a beautiful but unpredictable structure. A golf ball is manufactured with a precise size and shape and pattern. The dust around WR-124 looks more like a golf ball than a snowflake, and that is deeply, fundamentally puzzling. The implications of this extend far beyond WR-124 itself. Every galaxy in the universe is filled with dust. That dust plays a critical role in the formation of stars and planets. It shields newborn stars from their own radiation. It provides the material from which planets coalesce. It is the canvas upon which the story of cosmic evolution is painted. And the dominant sources of that dust are thought to be supernovae and evolved stars like Wolf-Rayets. If our understanding of how Wolf-Rayet stars produce dust is fundamentally wrong, then our understanding of the entire dust budget of the universe is wrong. This has ripple effects into cosmology, into galaxy evolution, into the study of planet formation. We are not just rewriting one chapter of astrophysics. We are potentially rewriting the entire book. There is another dimension to this mystery that deserves attention, a dimension that speaks to the very nature of scientific discovery. When the Webb team first saw these images, there was a moment of pure, unadulterated shock. The data processing pipeline ran its course, the images were assembled, and the scientists gathered around their screens to see what their months and years of effort had produced. And what they saw was not what they expected. The reaction, as described in interviews, was not a quiet nod of confirmation. It was a collective gasp. It was that rare, precious moment in science when you realize that nature has been hiding something from you, and that you are the first person in human history to see it. That moment of wonder, of terror, of exhilaration, is what drives the entire scientific enterprise. It is the reason we build telescopes like Webb. It is the reason we spend billions of dollars and decades of labour to push back the frontiers of the unknown. And the frontier is expanding. The questions that WR-124 has raised are now the subject of intense theoretical work. Physicists are scrambling to develop new models of dust formation that can account for what Webb has seen. Some are exploring the possibility that magnetic fields play a much larger role than previously thought. A magnetic field threading through the stellar wind could guide the formation of dust, organizing the clumps and filaments into the patterns we see. Others are investigating the possibility of radiative instabilities, complex feedback loops between the star's intense radiation and the dust itself. Perhaps the dust, once it forms, actually shields itself from the star's radiation, creating pockets of safety where more dust can grow. Perhaps the process is self-reinforcing, a runaway cycle of dust formation that defies the simple equilibrium models we have relied on. These are speculative ideas, but they are now on the table, being actively debated and refined. The data from Webb has opened the door, and the theorists are rushing through it. There is also the tantalizing possibility that the answer lies in the nature of the dust itself. Not all dust is the same. The composition of the grains, their size, their shape, their porosity, all of these factors influence how they interact with radiation. Perhaps the dust around WR124 is made of a material that is far more resilient than the carbon and silicate grains we have assumed. Perhaps it forms in a different crystalline structure, one that can withstand higher temperatures and more intense radiation. Or perhaps the grains are not solid at all, but fluffy, fractal structures with a huge surface area and a low overall density. Such grains could be surprisingly robust, able to survive conditions that would vaporize a solid grain of the same mass. This is another active area of research. Webb spectra, not just its images, hold the key. The telescope can analyze the light from the nebula, breaking it into its component colors, to reveal the chemical fingerprint of the dust. Those spectra are still being analyzed, and they may hold the answer. The story of WR124 is in the end a story about the limits of human knowledge, and about what happens when those limits are pushed. We built the most powerful telescope ever conceived, a machine of staggering complexity and cost, to answer fundamental questions about the universe, and in doing so, we discovered that we did not even know the right questions to ask. The telescope has done its job. It has shown us something new. It has shown us a mystery, a beautiful, confounding and profound mystery. The ice cube is sitting in the furnace, and for the first time we have a clear view of it. It is up to us now, to the generations of scientists who will follow, to figure out how it got there. That is the work. That is the joy. That is the endless, humbling, and glorious pursuit of understanding the cosmos that gave us birth. And it all started with a dying star, 21,000 light-years away, shedding its final tears of dust, and defying everything we thought we knew. And so we find ourselves here, standing on the shoulders of a dying star, staring into a cloud of dust that shouldn't exist. But it does. And that changes everything, because the dust we're talking about isn't just some cosmic nuisance that gets in the way of a pretty picture. It is the stuff of life itself. Literally, every single atom in your body that isn't hydrogen or helium was cooked in the heart of a star that lived and died long before our sun was even a glimmer in the galaxy's eye. That iron in your blood that makes it red, the calcium in your bones that holds you upright, the oxygen you just breathed in without a second thought, all of it was forged in stellar cores blasted into space by supernovae, or, as we are now learning, gently shed by massive stars as they waste away. We are not just stardust as a poetic metaphor. We are stardust as a literal physical fact, and the only reason we get to have this conversation, the only reason there are planets to stand on and oceans to drink from, is because of dust. Cosmic dust. It is the raw material of everything solid in the universe. Every moon, every asteroid, every rocky world, every mountain range on Earth. It all started as microscopic grains of dust, floating in the void, waiting for gravity to pull them together. So when I say that the James Webb Space Telescope found something impossible inside a dying star, I am not exaggerating. We are talking about the very foundation of how the universe builds its children. The star in question is a Wolf-Rayet, a rare and violent beast. Its official name is WR124, and it sits about 21,000 light-years away in the constellation Sagitta. It is a star in its death throes, burning through the last of its nuclear fuel at a ferocious rate. And for decades, astronomers have suspected that stars like this one could be major factories for cosmic dust. It made sense on paper. Wolf-Rayet stars blow off massive amounts of material, shedding their outer layers in powerful winds that scream out into space at millions of miles per hour. All that material, rich in heavy elements like carbon and oxygen, should be perfect for forming dust grains. But there was a problem, a massive, glaring, stubborn problem. The radiation from a Wolf-Rayet star is absolutely brutal. It is so intense that it should rip apart any newly formed dust grain, before it has a chance to grow. Imagine trying to build a sandcastle in the middle of a hurricane. That is the environment inside the wind of a dying Wolf-Rayet star. The radiation pressure is so strong that any tiny clump of atoms trying to stick together should be instantly blasted apart. So for years, the theoretical models said that Wolf-Rayet stars could not be significant dust producers. The math said no, the physics said no, but the universe, as it so often does, did not care about our math. The Hubble Space Telescope had given us hints. It saw something around WR1T4, some kind of nebulosity, some evidence of material piling up. But Hubble sees mostly invisible and ultraviolet light. It could not see the thermal glow of cold dust. Dust grains, especially the kind that form around these massive stars, are relatively cool. They glow in infrared, a part of the spectrum that Hubble is not optimized for. So we knew something was there, but we could not measure it. We could not count it. We could not weigh it. It was like seeing smoke in the distance and trying to guess how many trees were burning. You could make an educated guess, but you could not be sure. That is where the James Webb Space Telescope changed the game entirely. Webb was built for this. Its primary mirror is enormous, 6.5 meters across, and it operates at temperatures just a few degrees above absolute zero. It is designed to see the infrared universe with a clarity that no telescope before it has ever achieved. And when it turned its eye toward WR124, it did not just see a hint of dust. It saw a cosmic inferno of grain formation happening in real time. What Webb detected was utterly staggering. Around this single dying star, there is a shell of newly formed dust that contains the equivalent of about 10 Earth masses of material. 10 Earth's worth of dust. And here is the kicker. That dust did not accumulate over millions of years. The observations show that it was produced in a cosmic blink of an eye, over just a few thousand years at most. For a star that lives for millions of years, that is practically overnight. In the time it took human civilization to invent agriculture, build cities, and land on the moon, this star blew off enough material to build 10 entire rocky planets. That is not just impressive. That is paradigm-shattering, because if Wolf-Rayet stars can produce dust that fast and that efficiently, it means we have completely underestimated the role they play in the chemical evolution of the universe. And that has direct, immediate and profound consequences for one of the biggest puzzles in modern cosmology, the problem of dust in the early universe. When we look back at the most distant galaxies, the ones we see as they were just a few 100 million years after the Big Bang, we expected them to be pristine. We expected them to be made mostly of hydrogen and helium, with very little in the way of heavy elements and dust. That is the logical assumption. You need many generations of stars to live and die to produce significant amounts of dust. You need time, but when we actually look at these ancient galaxies with telescopes like the James Webb, we find something completely different. They are dusty, shockingly dusty. Some of these galaxies have as much dust as the Milky Way, and they are less than 1 billion years old. That is a problem, because the standard models of cosmic dust production, the ones based on supernovae and asymptotic giant branch stars, simply cannot produce enough material quickly enough to explain what we are seeing. There is a gap in the budget. A missing source of dust that the universe seems to have found, but we had not. WR124 may be the answer. Wolf-Rayet stars are massive, they live fast and they die young. But before they die, they can pump out enormous quantities of dust in a very short time. If there were enough of these stars in the early universe, and there is no reason to think there weren't, then the dust problem starts to make sense. Think about it. The first stars in the universe were enormous. They were hundreds of times the mass of our Sun, and they lived for only a few million years before exploding. Those first stars, the so-called population 3 stars, would have produced a lot of heavy elements, but the subsequent generations of stars, the ones that formed from that enriched material, may have included a high proportion of Wolf-Rayet stars. We do not know exactly how many, because we cannot see them individually at such distances. But the dust we see in those early galaxies has to come from somewhere, and now we have a direct observation of a Wolf-Rayet star doing exactly what we need it to do, producing dust at a furious rate. It is a smoking gun. It is the missing link in the chain of cosmic recycling, and it changes how we model the formation of everything from planets to galaxies to life itself. But this discovery does more than just fill a gap in a spreadsheet. It reshapes the story we tell about our own origins. Because if Wolf-Rayet stars are the major dust factories we now suspect them to be, then they are also the factories of the raw material for planets like Earth. Every grain of dust that came together to form our world, every atom of carbon in your body, every speck of silicon in the sand beneath your feet passed through environments like the one around WR's 124. That is the connection. That is the thread that ties a dying star 21,000 light-years away to the very keyboard you are typing on right now. It is humbling and it is beautiful. And it all hinged on a single question. Could dust survive the brutal environment around a Wolf-Rayet star? Webb answered that question with a resounding yes. Not only does it survive, it thrives. It accumulates. It builds up into massive clouds that will one day drift through space, cool down and become part of new stars and new planets, and somewhere out there, possibly new life. There is another layer to this story that we often overlook. It is about the nature of scientific discovery itself. For decades, Wolf-Rayet stars were a curiosity. They were weird, messy, hard to study, and they did not fit neatly into the clean narratives of stellar evolution that we taught in introductory astronomy classes. They were the problem children of the cosmos. And because they were hard to study, we made assumptions. We assumed that they could not produce much dust, because our models said so. We assumed that the numbers would never add up. We assumed that the universe would behave according to the neat, tidy laws we had written down. But the universe is not neat. It is not tidy. It is messy, violent, and full of exceptions. And every time we think we have it figured out, something like WR124 comes along and reminds us that we are still beginners. We are still standing on the shore, dipping our toes into an ocean of unknowns. And that is not a weakness. That is the point. The James Webb Space Telescope was not built to confirm what we already know. It was built to show us what we did not know we did not know. And in the case of WR124, it did exactly that. It revealed a process that we had dismissed as unlikely, happening at a scale we had not predicted, in a time frame that seemed impossible. And now we have to go back to the drawing board. We have to rewrite the textbooks. We have to adjust our models of galaxy formation and chemical enrichment. That is the work of science. It is not about being right all the time. It is about being willing to be wrong. It is about following the evidence, even when it leads you somewhere uncomfortable. And right now, the evidence is pointing directly at Wolf-Rayet stars as unsung heroes of the cosmic dust cycle. So what does this mean for the future? It means that when we look at the earliest galaxies with Webb, we will have a new tool to interpret what we see. We will be able to say, with more confidence, that the dust in those galaxies probably came from stars like WR124. We will be able to build more accurate models of how the first rocky planets formed. And we will be able to ask new questions. If Wolf-Rayet stars are so efficient at making dust, what about other types of massive stars? What about the very first stars that ever existed? Could they have been even more efficient? The answers are out there, waiting for us in the infrared glow of distant suns. And with every new observation, with every new image from Webb, we inch closer to understanding the grand interconnected story of how the universe went from a hot, formless soup of particles to a place where a curious species could evolve, build telescopes, and ask where it all came from. That is why this discovery matters. It is not just about dust. It is about our place in the cosmic order. It is about the realization that the universe is not a machine running on predictable laws that we have fully grasped. It is a living, evolving, wildly creative system that constantly surprises us, and we get to be part of that surprise. We get to be the ones who look at the data, scratch our heads, and say, well, that changes everything. That is the human experience of science. It is messy, it is frustrating, and it is glorious. And right now, it is happening faster than ever before. The James Webb Space Telescope has only been operating for a short while, and it has already turned our understanding of the cosmos upside down. We have found galaxies that should not exist. We have found dust that should not be there. And we have found that the universe is far more efficient at building the raw materials for life than we ever gave it credit for. So the next time you look up at the night sky, remember the dust. Remember that it is not just empty space up there. It is a factory. It is a nursery. It is a graveyard and a birthplace all at once. And remember that a single dying star 21,000 light years away just told us something profound about how the universe works. It told us that we were wrong. And that is not a failure. That is the greatest gift science can give. Because every time we discover that we were wrong, we are one step closer to the truth. And the truth, as it turns out, is that we are made of the impossible. We are made of dust that survived against all odds. We are made of atoms that were forged in violence and shaped by time. And we are only just beginning to understand how it all came together. That is the journey. That is the mystery. And that is why the dust matters more than you could ever imagine. The impossible amount. Conflict with models. Let's be real for a second. If you had asked any astrophysicist on the planet just a few years ago what the James Webb Space Telescope would find inside a dying star, they would have given you a very polite, very confident answer. They would have said something like, well, we expect to see a little bit of dust, maybe a few % of the star's mass converted into grains, but nothing crazy. The physics is pretty clear. And they would have meant it. They weren't being arrogant. They were just following the rules. The rules of stellar physics, I mean. Rules that have been tested and refined over decades. Rules that have worked beautifully for everything from the smallest red dwarfs to the most massive supergiants. Rules that apparently are about to get torn up and rewritten in real time. Because here's what Webb actually saw. It saw dust. A lot of dust. An impossible amount of dust. And I don't use that word lightly. When scientists say something is impossible, they usually mean it's extremely unlikely, or it violates a well-established theory, or it would require a miracle to explain. In this case, they mean it literally violates the fundamental understanding of how matter behaves around a dying star. The standard model, the one that has been taught in every astronomy classroom for the last 40 years, says that radiation pressure from the star should push any newly formed dust grains outward, away from the star, and destroy them in the process. It's like trying to build a sandcastle in the middle of a hurricane. The grains just don't have time to stick together before they get blasted apart. The math is brutal. It says that for every 100 units of material that the star expels into space, only 1 to 3 units should ever become dust. That is the predicted efficiency. 1 to 3%. That is the ceiling. That is the maximum. And everyone just accepted it. Because it made sense. Because it was consistent with everything we knew. Because it was the kind of clean, elegant physics that makes the universe feel orderly. But Webb doesn't care about clean and orderly. Webb cares about what is actually happening out there. And what Webb found was an efficiency that is 10 times higher than predicted. 10 times. Not a little bit higher, not a marginal adjustment, not a rounding error that you can fix with a tweak to the model. We are talking about an efficiency of something like 30%, maybe even higher, depending on which region of the star you look at. That is not just a challenge to the existing models. That is a frontal assault on everything we thought we knew about the life cycle of stars. And the really unsettling part is that we don't have a single clean explanation for it. We have multiple hypotheses, each one plausible, each one with its own strengths and weaknesses, and each one requiring a fundamental rethinking of how dust forms in extreme environments. Let me walk you through these ideas, because this is where the story gets genuinely fascinating. The first hypothesis is all about clumping instabilities in the stellar wind. Now, a stellar wind is not like a gentle breeze. It is a torrent of charged particles and gas streaming away from the star at hundreds of kilometers per second. Under normal circumstances, that wind is relatively uniform, and any dust that tries to form gets shredded immediately. But if the wind becomes clumpy, If it develops dense pockets of gas that are shielded from the star's most intense radiation, then those pockets become safe havens where dust can grow. The gas in those clumps is so thick that the radiation can't penetrate it all the way. It's like hiding behind a boulder during a sandstorm. The boulder takes the brunt of the wind and you stay safe in the lee of it. In the same way, these dense clumps of gas provide a shadow, a temporary sanctuary where dust grains can nucleate and grow without being immediately vaporized. And here is the kicker. Webb's images of that dying star, the one we have been talking about, show exactly this kind of clumpy structure. The images are not smooth and uniform. They are lumpy and irregular, with knots of material that look like they are being ejected in uneven bursts. That visual evidence strongly supports the clumping hypothesis, but it is not proof. It is a clue. It is a tantalizing hint that the star's wind is far more chaotic than we ever imagined. The second hypothesis involves a binary companion. See, a lot of massive stars are not alone. They have a partner, another star orbiting around them, sometimes close, sometimes far, and if that companion is close enough, it can disrupt the geometry of the stellar wind in profound ways. Instead of a spherical outflow, you get a warped, asymmetric mess. The companion star strips material from the main star, creating streams and sheets of gas that follow weird paths. In those shadowed regions, behind the companion or in the wake of its orbit, the radiation pressure is greatly reduced. Dust can form in those quiet zones, accumulating over time. It is a messy, dynamic process, and it is hard to model accurately because the orbital parameters are usually unknown. But it is a very plausible explanation for why we see so much dust. The companion star essentially acts as a cosmic shield, carving out safe spaces for dust to coalesce, and we know that many dying stars are part of binary systems. It might not be an exception, it might be the rule, and if that is true, then we have been massively underestimating the role of binary interactions in dust production for decades. Then there is the third hypothesis, which is almost geological in its simplicity. It suggests that the dust grains are simply growing faster than they can be destroyed. Imagine that the standard model assumes a certain growth rate, based on the density and temperature of the surrounding gas. But what if the growth rate is actually much higher? What if the grains have some way to accelerate their own formation, perhaps by electrostatic forces, or by merging with other grains in the turbulent wind? This would mean that the dust is not a passive passenger in the outflow. It is an active participant, grabbing onto every available atom and clinging to life with stubborn tenacity. In this scenario, the grain growth outpaces the destructive radiation pressure. The dust builds up faster than the star can tear it down, and the efficiency jumps from 3% to 30% in a hurry. This idea is appealing because it does not require any exotic new physics. It just requires that we have underestimated how quickly dust can form under the right conditions. But it also raises a difficult question. If the growth rate is so high, why haven't we seen evidence of it in other stars? The answer might be that we haven't been looking with the right instrument. And Webb is the right instrument. It is the first telescope that can actually see the early stages of dust formation with enough resolution to measure the grain sizes. The fourth and final hypothesis for now is that the dust is forming in a cool equatorial disk, not in the stellar wind itself. This is a subtle but crucial distinction. A dying star, like the one Webb observed, can sometimes shed material in a disk, a rotating ring of gas and dust that orbits the star in the same way that a protoplanetary disk orbits a young star. In this disk, the density is much higher, the temperatures are lower, and the radiation from the star is partially blocked by the disk itself. It is a dust factory, a place where grains can grow large and survive for long periods of time. The disk shields its own interior. It creates a self-sustaining environment where dust formation is not just possible, it is inevitable. And Webb's images do show a structure that looks suspiciously like a disk, a flattened ring of material around the star's equator. If this is indeed a disk, then it changes the entire conversation. Instead of trying to explain how dust survives in the harsh wind, you simply accept that most of the dust never enters the wind at all. It stays in the disk, protected, until the star's final convulsions scatter it into space. This hypothesis elegantly bypasses many of the problems that plague the other models. But it also requires that the star is rotating fast enough to create such a disk, and that the disk is stable enough to last for thousands of years. We do not know if that is the case yet. We need more data. We need more observations. We need more time. And that is the crazy thing. All 4 of these hypotheses are on the table. None of them have been ruled out, and none of them are mutually exclusive. It is entirely possible that all 4 mechanisms are operating simultaneously, each contributing a fraction of the total dust. A clumpy wind, a binary companion, rapid grain growth, and a cool equatorial disk could all be working together to produce the impossible amount of dust that Webb detected. The universe does not play favourites. It uses every trick in the book, and we, the humble theoreticians, are left scrambling to catch up. The response from the scientific community has been nothing short of extraordinary. Within weeks of the first Webb images being released, teams of theoretical physicists around the world began revising their models. They threw out their old assumptions. They rewrote their simulations from scratch. They ran new calculations that incorporated clumping, binary interactions, growth rates, and disk geometries. And many of them had to admit that their previous models were simply invalid. Not a little bit wrong. Completely and utterly wrong. Decades of work, tens of thousands of research papers, all based on an assumption that has now been disproven by a single set of infrared images. That is humbling. That is science at its most brutal and beautiful. And it is happening right now as we speak. The debate is fierce, but it is also incredibly productive. Scientists are arguing with each other in the hallways of conferences, in the comment sections of preprint servers, in late-night video calls that stretch across time zones. They are proposing new observations, new ways to test the hypotheses, new simulations that can be run on supercomputers. Some of them are betting on the clumping model. Others are convinced that the binary companion is the key. A few are sticking with the disk idea. And a handful are quietly wondering if there is something even more fundamental that we are missing. Something about the nature of dust itself that we have not yet discovered. The truth is, we are in the early days of a revolution, and revolutions are messy, they are chaotic, they are full of wrong turns and dead ends, but they are also exhilarating. And here is a bit of historical context that puts everything into perspective. This mystery, the mystery of how dust forms around dying stars, has been unsolved for 40 years. 4 decades. That is a lifetime. The first hints of the problem emerged in the early 1980s when astronomers pointed the Infrared Astronomical Satellite, or IRAS, at the sky and discovered that many dying stars had far more dust than anyone expected. The signal was clear, but the resolution was too low to understand the details. For 40 years we have known that something was off. For 40 years we have been working with models that we knew were incomplete, but we had no way to fix them. We were blind, we were groping in the dark, and then Webb opened its eyes. It did not just confirm the anomaly, it smashed it wide open. It gave us the resolution, the sensitivity, the spectral data that we needed to finally start testing the hypotheses. And what we have learned in just a few months has already upended an entire field. The dream of every scientist is to live through a moment like this. A moment when the data finally arrives, when the answers start flowing, when the old models crumble and the new ones take shape. Right now, we are living in that moment. So, let's not pretend that we have this figured out. We don't. The dust is winning. The star is producing 10 times as much dust as it should. The models are broken. And the most exciting part is that we get to watch the repair process in real time. We get to see the arguments, the breakthroughs, the dead ends, and the eureka moments as they happen. The scientific method is not a dry, boring process. It is a human drama, full of passion and frustration and joy. And right now that drama is unfolding around a single dying star. A star that was supposed to be ordinary. A star that turned out to be anything but ordinary. This is not the end of the story. It is the beginning of a new chapter. and we are here to witness it. We are not just living through a moment of new data. We are living through a paradigm shift, a fundamental reordering of the cosmic accounting ledgers. For 40 years, the standard model of stellar dust formation was not just the best explanation we had. It was the only explanation. It was a model born from the limitations of our instruments as much as from our theoretical insights. We built our entire understanding of galactic evolution, of how galaxies recycle their material from generation to generation of stars, on that shaky foundation. And now, Webb has revealed the cracks, not as hairline fractures, but as gaping chasms. The implications are staggering. Let us first examine the structure of an asymptotic giant branch star, the type of star that is the primary source of this cosmic dust problem. A star like this is a late-stage giant, a massive, swollen and dying engine. Its core is a dense ball of carbon and oxygen, inert and awaiting its final fate. Above that core, layers of helium and hydrogen are undergoing episodic fusion, like a series of sporadic explosions. This pulsation is key. It drives the star's outer envelope to expand and contract, creating shockwaves that pulse through its atmosphere. These shockwaves lift material from the star's photosphere, ejecting it into space in a series of rhythmic gusts. This ejected material is a rich soup of atoms: carbon, oxygen, silicon, iron, magnesium, and a host of trace elements forged in the star's nuclear fires. This is the raw material for dust. The standard model assumed that this material, once ejected, would be immediately subjected to the full force of the star's radiation field. The star is incredibly luminous, and its light carries momentum. Any grain that begins to form, any clump of atoms that starts to stick together, will be struck by photons. Those photons exert a pressure, a tiny push. For a small grain, that push is enough to accelerate it away from the star at tremendous speeds. The grain is then exposed to the harsh ultraviolet radiation of the interstellar medium, which can destroy it, or it is simply carried so far away that it cannot interact with the dense gas near the star where growth is possible. The model predicted that only a tiny fraction of the ejected gas, the 1 to 3% we discussed, would ever find the perfect conditions to survive and grow into grains large enough to be stable. The rest would be wasted, remaining as gas forever. But Webb's observations of this particular star, a star we call a carbon-rich AGB star, show a completely different reality. Instead of a dilute, uniform wind, Webb's spectrographs and images reveal a complex filamentary structure. There are dense knots of gas, some of them containing molecules like silicon carbide and carbon monoxide, which are the building blocks of solid grains. These knots are not moving at the uniform speed predicted by the standard model. They are slow, they are clumpy, they are staying close to the star for far longer than they should. This is the observational bedrock of the clumping instability hypothesis. The star is not producing a gentle, continuous breeze. It is producing a series of violent, discrete outbursts, like a cosmic cough. Each cough creates a dense shell of gas that is temporarily shielded from the star's radiation by the gas itself. Inside these shells, the density is so high that the grains can nucleate and grow without being blasted away. The historical parallel here is deeply instructive. In the 1960s, radio astronomers discovered quasars, incredibly bright and distant objects. The standard model of the time, based on stellar physics, could not explain their energy output. Objects that bright should not exist. The calculations said that a star would have to be impossibly massive to produce such light. It took a decade of heated debate, multiple observational campaigns, and a willingness to throw out old assumptions before the true explanation emerged. Quasars are not stars at all. They are supermassive black holes at the centers of distant galaxies, actively accreting matter and converting gravitational potential energy into radiation with an efficiency far beyond anything a star could achieve. The models were not just wrong, they were fundamentally misdirected. We are standing at a similar precipice now with dust formation. The models are not just underestimating the dust yield, they are likely missing the entire physical mechanism that drives it. Consider the binary companion hypothesis. This is not a fringe idea. it is supported by a vast body of observational evidence that many, if not most, massive stars have companions. For decades, we treated these binaries as a nuisance, a complication in our models. We averaged out their effects, assuming that over time, the binary interaction would not significantly alter the total dust production. That was a convenient assumption, but it was also a lazy one. Webb's images now show clear asymmetries in the dust shell around this dying star. There are arcs and spiral structures that are the telltale signature of a binary system. The companion star, perhaps a white dwarf or a low-mass main sequence star, is carving a cavity in the wind. It is creating a gravitational wake, a region of enhanced density, and reduced radiation pressure where dust can form in abundance. The companion is not just a passive bystander. It is an active sculptor, reshaping the outflow and dramatically boosting the dust yield. The implications for galactic evolution are profound. Every galaxy is filled with dying stars. If the standard dust yield is off by a factor of 10, then our models of how galaxies enrich their interstellar medium with heavy elements are off by the same factor. Dust is not just a pretty feature of the universe. It is the primary coolant for star-forming gas clouds. It shields new stars from radiation. It provides the surface area for the formation of complex molecules, the precursors to life. If there is 10 times more dust out there than we thought, then the universe is a much dirtier, more complex, and more fertile place than we ever imagined. The star formation rates we calculate, the chemical evolution of galaxies we model, the very timeline of when the first planets could have formed all hinge on this single, seemingly obscure process of dust creation in the winds of dying stars. And so, the debate continues. We do not know which of the 4 hypotheses, or which combination of them, will ultimately prevail. Perhaps it is a new mechanism entirely, something we have not yet conceived. The data from Webb is still being analysed. More observations are scheduled. We will point the telescope at other dying stars, at stars with different masses, different compositions, different evolutionary states. We will compare their dust shells. We will look for binary companions. We will measure the clumpiness of their winds. And slowly, painstakingly, we will build a new model. It will be a messy process. There will be false leads and dead ends. There will be arguments and retractions and moments of triumph. But that is the nature of real science. It is not a collection of settled facts. It is a living, breathing, evolving conversation between theory and observation. And right now, the conversation has just become a lot more interesting. The impossible amount of dust is no longer an anomaly to be explained away. It is a revelation. It is a window into a universe that is far more dynamic, far more chaotic, and far more capable of creating the raw materials of life than we ever dared to believe. Before Webb, we were looking at the universe with one eye closed, or rather, with an eye that could only see the broadest, blurriest shapes in the dark. The Spitzer Space Telescope was a marvel in its own right, a true pioneer. It gave us our first real peek at the infrared universe, revealing things visible light simply could not show us. But its vision was, shall we say, a little coarse. Think of it like trying to read a book from across a football field. You might see that it is a book. You could probably tell if it was open or closed, but you would never catch the nuance of the paragraph, the weight of a single word, or the exquisite detail of the ink on the page. Spitzer had a resolution that struggled to untangle the chaotic knots of dust and gas around a star like Wolf-Rayet 124. It saw the dust, yes. It knew it was there, but it could not see the shape of the storm. It could not count the grains. And that is where the middle of the infrared spectrum becomes a kind of sweet spot. We are talking about wavelengths between about 5 and 28 microns. In that range, warm dust glows like a hot coal. It absolutely dazzles. This is the region where the universe's industrial heart is laid bare, where stars are born and where they die, leaving behind their most precious residue. But to see this glow with any clarity, you need an instrument that is not just good, but inhumanly sensitive. You need the mid-infrared instrument on the James Webb Space Telescope, or MIRI, as the scientists call it. And when I say sensitive, I do not mean a little bit better than what came before. I mean that Miri is roughly 1,000 times more sensitive than any mid-infrared instrument we have ever launched. 1,000 times. That is not an incremental improvement. That is a paradigm shift. It is the difference between squinting at a firefly from a mile away and being able to count the hairs on its back. That leap in capability is the sole reason we are having this conversation about a dying star. Without Miri, the dust inside WR 124 would have remained a vague rumour, a statistical blip. With it, it became a landscape. Now let that sink in for a moment. The photons that Miri captured, the tiny packets of infrared light that painted this picture, did not just arrive here casually. They are travellers, they are pilgrims on a journey that has taken them 15,000 years. Let me put that in human terms. 15,000 years ago, there were no cities, there were no farms, there were no written words. The last ice age was still retreating its icy fingers from the northern hemisphere. And at that exact moment, a photon was born in the blazing heart of a Wolf-Rayet star, deep in the constellation Sagittarius. It began its silent, relentless crawl across the cosmos, moving at the speed of light, passing through clouds of gas, skirting the edges of other galaxies, racing through the void. It did not stop. It did not slow down. It travelled 15,000 light-years to reach the gold-plated mirror of the James Webb Space Telescope. And here is the kicker. That star, the star that gave birth to that photon, may already be dead. It might have exploded in a supernova 10,000 years ago. It could have collapsed into a black hole. We have no way of knowing yet. But because when we look at WR 124, we are not seeing it as it is now. We are seeing it as it was when mammoths still roamed the earth. Every image Webb sends back is a message in a bottle from the deep past. We are not observers of the present. We are archaeologists of light. Achieving this kind of vision is not just a matter of building a bigger mirror, although the 6.5-metre mirror certainly helps. It is a battle against heat, and I mean a literal, brutal, unrelenting war against the very concept of warmth. You see, an infrared telescope is fundamentally different from the one in your backyard. For Webb to see the faint heat signatures of distant stars and their dust, its own heat must be virtually non-existent. If the telescope itself is warm, it will drown out the very signal it is trying to detect. It is like trying to hear a whisper in a room full of people shouting. So, Webb engages in a form of cryogenic engineering so extreme it borders on the fantastical. Its detectors, the very eyes of Miri, must be kept colder than the objects they are observing. We are talking about temperatures hovering just a few degrees above absolute zero, around minus 266 degrees Celsius. That is colder than the surface of Pluto. It is colder than the empty void of deep space itself. To achieve this, Webb carries a massive sunshield the size of a tennis court, a 5-layer blanket designed to reflect the sun's relentless energy away. And even then, it needs a dedicated cryocooler, a kind of super-powered refrigerator, to keep Miri chilled to its operating temperature. Every single joule of heat is the enemy. Every stray photon from the spacecraft itself is a contaminant. The engineering team had to design a machine that could effectively observe the universe while hiding from its own shadow. Once these precious photons are captured, once the detectors have registered their arrival, the data has to get home. And that brings us to another marvel of engineering, the Deep Space Network. Imagine a whisper sent from a campfire on the other side of the world, and you have to shout it back across the entire solar system. Webb does not have a direct cable connection. It talks to Earth using a radio signal, a faint focused beam of energy travelling for hundreds of thousands of miles. The Deep Space Network is a collection of 3 massive radio antennas, strategically placed around the globe, that are constantly listening. They are the ears of humanity, cocked toward the heavens. When Miri or NIRCam finishes an observation, it beams its data to one of these antennas. It is a slow, painstaking process, a trickle of data from a torrent of discovery. And that data is raw. It is a string of numbers, a table of intensities for each pixel. It contains no colour. It contains no beauty. It is just numbers. So where do the colours come from? The answer is honest, and it might surprise you. The colours are not real. They are a translation. Human eyes cannot see infrared light. We are biologically blind to it. So, when the scientists process the image of WR124, they have to assign visible colours to the invisible wavelengths. It is a kind of artistic cartography. Short infrared wavelengths might be assigned blue. Longer ones might become red or green. The brilliant, glowing structures you see in the final image are a map of temperature and composition, painted in the palette of human vision. The reds and oranges you see swirling around the star, that is the coolest, dustiest material. The blues and whites, that is the incredibly hot plasma and gas erupting from the star itself. It is not a photograph. It is a data visualization. It is a portrait of a star where we chose the colours to tell its story. And you know what? It is even more beautiful that way, because every hue carries a specific physical meaning. And this is where the true genius of Webb comes into play. An observation of a star like WR124 is rarely a one-instrument affair. It requires coordination. It requires teamwork on a cosmic scale. For this single stunning image, Webb had to combine exposures from two entirely different instruments, NIRCam, which sees in the near-infrared, and MIRI, which sees in the mid-infrared. Think of it like a painter who uses both a fine brush and a roller. NIRCam provides the sharp, crisp details, the edges, the structure of the gas, and the sharp points of hot plasma. MIRI provides the depth, the glow of the dust, the warm, ambient light of the star's slow death. The team behind the scenes had to schedule separate observations, calibrate each instrument separately, then merge the data into a single, cohesive mosaic. This is a technical achievement that spans continents, time zones, and years of careful planning. It is not just pointing a telescope and clicking a button. It is a symphony of human collaboration, all aimed at a single point in the sky. So, as you look at that image of the dying star, I want you to remember the engineering that made it possible. Remember the cryocooler, working silently in the vacuum of space, fighting a constant battle against the heat of a sun 1.5 million kilometers away. Remember the gold mirrors, polished to such perfection that they can capture a single photon that has been travelling for 15 millennia. Remember the deep space network, listening for that faint whisper. Remember the scientists who looked at a sea of numbers and chose to paint them red, blue, and gold. Because that image is not just a picture of a star, it is a monument to human ingenuity. It is proof that we, a species on a pale blue dot, can reach out and touch the edge of eternity. And the discovery it contained, that impossible, catastrophic flood of dust, was not a lucky accident. It was a direct result of this technological mastery. It was a secret that the universe kept for 15,000 years, and we finally had the key to unlock it. For 15,000 years, that light was travelling. A marathon across the cosmos, racing past star systems that were born and died while it was still on its way. And when it finally hit the mirror of the James Webb Space Telescope, it didn't just solve a mystery about one dying star. It shattered a puzzle that had been staring astronomers in the face for decades. A puzzle about the very first galaxies in the universe. You see, when we look back to the earliest epochs of cosmic history, to a time just 700 million years after the Big Bang, we see something utterly baffling. We see galaxies that are absolutely bursting with dust. And I mean vast, enormous quantities of the stuff. Dust that, by all the old rules, simply should not be there. It was a cosmic inconsistency, a nagging thorn in the side of astrophysics, because the primary sources of dust in the modern universe are supernovae, the violent explosions of massive stars. But in those early pristine times, the universe was metal poor. It had only a few generations of stars under its belt. Standard supernova models simply could not churn out dust fast enough to explain what we were seeing. The math didn't work, the timeline didn't work. It was like walking into a freshly painted room and finding a mountain of ancient sawdust in the corner with no carpenter in sight. That puzzle, that impossible observation, stood as one of the great unanswered questions of modern cosmology. How did the early universe get so dusty so fast? It was a problem that forced theorists to scramble, to invent exotic scenarios. to wonder if our understanding of star formation and stellar death was fundamentally broken. And then James Webb looked at a star, not a galaxy at the edge of time, but a star right here in our own galactic backyard, a star called WR124, a Wolf-Rayet star, and it found that star pumping out dust at a rate that was frankly ridiculous. It was a factory, an impossibly efficient cosmic dust factory, and that, right there, was the missing link. Wolf-Rayet stars, these strange, massive beasts with their furious winds and stripped exteriors, were the carpenters we had been looking for. They were the missing piece of the early universe dust budget. For decades, astronomers had been scratching their heads, wondering where the dust in those ancient galaxies came from, and for decades they had been underestimating the power of these rare, violent stars. The data from WR124 slammed the gap shut. It resolved a decades-long inconsistency in one clean, elegant stroke. This is the incredible thing about the James Webb Space Telescope. It doesn't just look at the faintest, most distant objects in the sky. It looks at things next door, things in our own cosmic neighbourhood, and uses them to decode the past. Webb studies both the dying stars in our own galaxy and the ancient galaxies on the other side of the observable universe. And the data from one of those studies, the data from WR124, directly informs the interpretation of the other. It is a bridge across time. The dust we see pouring out of this nearby Wolf-Rayet star is the exact same kind of dust that was seeding the first generations of galaxies, the same processes writ large, the same cosmic engine running on the same fuel, producing the same raw materials. And those raw materials are the key to everything. They are the seeds of the future. The dust from ancient Wolf-Rayet stars didn't just float around in space, a silent monument to a dead sun. It seeded the next round of star formation. It clumped together, forming the nursery clouds where new stars ignited, and around those new stars the dust gathered into disks that would eventually coalesce into planets. The dust from a dying star, a star that burned for maybe a few million years in the early universe, directly contributed to the formation of planets billions of years later, planets that might, just might, harbour life. And here is where the story gets really wild. Because it's not just dust. It's not just carbon and silicon and iron. It's chemistry. The nebula around WR124, the vast glowing cloud of its ejected material, contains complex organic molecules, polycyclic aromatic hydrocarbons, or pHs. Now don't let the boring name fool you. pHs are the precursors to the building blocks of life. They are the chemical stepping stones that lead to amino acids, which build proteins, and to nucleobases, which build DNA and RNA. These are not just molecules. These are the first tentative strokes of the cosmic paintbrush that, given the right conditions, can sketch out something that thinks, and breathes, and wonders about the stars. We found PAHs in the nebula of a dying star. In a region of space that looks like a violent, destructive explosion, we found the ingredients for life. The death of a star is not an end. It is a chemical transformation. It is a release. It is the universe scattering its most complex creations across the heavens, a wild, chaotic, beautiful act of generosity. The connection between a star like WR124 and the origin of life is not a metaphor. It is a literal, physical chain. The carbon in your body, the oxygen you breathe, the nitrogen that makes up the air, every single atom heavier than hydrogen and helium was forged in the heart of a star and then scattered into space by a stellar wind or a supernova. But the James Webb Space Telescope has now shown us that the process is even more intimate, that the dying star does not just scatter atoms, it scatters complex organic molecules. It doesn't just provide the bricks, it starts stacking them. So, what does this mean? It changes the way we think about the Drake equation. For those of you who don't spend your Friday nights calculating the probability of alien life, the Drake equation is a famous formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. One of its critical variables is the fraction of stars that have planets capable of developing life, and that fraction depends, in no small part, on the amount and the type of interstellar dust available to seed those planetary systems with the necessary organic compounds. Before Webb, our models for dust production were crude, incomplete, and based on observations that simply didn't have the resolution to see the full picture. The data from WR124 has given us a massive upgrade. It has shown us that Wolf-Rayet stars are far more efficient at producing complex organic dust than we ever imagined, which means that the early universe, the primordial broth, was richer, thicker, and more fertile than we thought. This has direct implications for the search for extraterrestrial intelligence, for SETI, because if cosmic dust factories like WR124 were common in the early universe, and if their dust seeded countless planetary systems with the precursors for life, then the probability of life emerging in the universe just went up, significantly. It doesn't mean we will find little green men tomorrow. It doesn't mean we will hear an alien radio signal tonight. But it does mean that the chemical foundation for life is not rare. It is not a fluke of a single star or a single planet. It is a byproduct of the normal, everyday death of massive stars. It is a common byproduct. And if the raw ingredients are common, then the cocktail is more likely to be brewed somewhere else. The cycle of cosmic dust is the engine of life's chemistry. It is the factory that grinds and refines the elements into ever more complex forms. And Webb has now connected the dying gasps of a massive star to the very first stirrings of life's raw materials. It is a direct optical link between stellar death and the origins of biology. That is not hype. That is data. We are looking at the chemical machinery of creation, and it is running inside a star that is exploding itself to pieces. When you stand outside on a clear night and look up at the Milky Way, you are looking at the dust, the dark patches, the rifts, the hazy bands of light. That is the stuff of life. That is the ash of 1 billion ancient stars. Wolf-Rayet stars that burned bright and died young, scattering their guts across the galaxy. We are made of that stuff. We are the product of that cycle. And what Webb has done, by staring at WR124, is write the user manual for the machine that made us. So, the impossible discovery inside a dying star was not just a story about a star. It was a story about us. It was a story about the first galaxies, and the planets that formed in their shadows, and the life that might have started on those planets, and the telescopes that we, a curious species on a small planet, built to look back and see our own origins. The early universe puzzle is no longer a puzzle. The missing dust is no longer missing. It was there all along, hidden in plain sight, waiting for us to build a machine powerful enough to see the truth. And the truth is beautiful. It is messy, it is violent, and it is full of hope. Because if a dying star can create the building blocks for life, then maybe life is not a miracle. Maybe it is just chemistry. The right chemistry, in the right place, at the right time. And thanks to James Webb, we now know that the universe has been brewing that chemistry for a very, very long time. The dust cloud around WR124 is a monument to a life that was, but it is also a nursery for a life that will be. The atoms that leave that star today will drift through the galaxy for millions of years. They will mix with other clouds, other debris, other leftovers from other stellar deaths. They will cool and clump and collapse. They will form a new star, and around that new star, a planet. And on that planet, maybe, a molecule will twist into a shape that can replicate itself. A shape that can remember. A shape that can wonder. And if that happens, if a life form on some distant world ever looks up at its own sky and sees a dying star, it will be looking at its own ancestor. It will be looking at the engine that made it possible. We have closed the loop. The mystery of the early universe's dust is solved. The implications for the emergence of life are profound, and the James Webb Space Telescope, the most ambitious machine we have ever built, is the historian that wrote the final chapter. The star exploded, the dust poured out, the telescope caught the light, and we, the children of the dust, finally understood where we came from. That is the story, and we are living in the middle of it. The impossible discovery inside a dying star was not an end. It was a beginning of a new understanding of our place in the cosmos, a place built on the ashes of 1 billion suns and the patient, relentless chemistry of a universe that is, in its own cold and violent way, trying to make something beautiful. And we are the proof that it is working. And it is working on a scale that we are only beginning to grasp. The data from WR124 does not just tidy up a loose end in our models. It rewrites the opening chapters of the cosmic story. For decades we operated under a comfortable assumption. We assumed that the early universe was a simple place, a place of hydrogen, helium, and a thin sprinkling of heavier elements cooked up in the first generation of stars, the so-called population 3 stars. We assumed that dust, the complex carbon-rich, silicate-rich material that dominates the interstellar medium of modern galaxies, was a latecomer, a product of many generations of stellar recycling, a luxury item that the young universe simply could not afford. That assumption is now dead. WR124 has killed it. This single star, a Wolf-Rayet star in our own galaxy, is ejecting dust at a rate that is orders of magnitude higher than what our old models predicted for any star, let alone a star in a metal-poor environment. And because Wolf-Rayet stars are short-lived, they do not linger. They do not wait. They explode or they blow off their outer layers in a frantic, desperate rush, scattering their chemically rich interiors across the cosmos in a geological instant. This means that the very first generations of stars, the ones that formed from the pristine gas left over from the Big Bang, could have included Wolf-Rayet stars, and if they did, they would have polluted the early universe with dust almost immediately. The timeline collapses. The impossible dust in those ancient galaxies is no longer impossible. It is inevitable, but the implications go deeper. They go into the very mechanics of how galaxies form and evolve. Dust is not a passive bystander in a galaxy. It is an active participant. It is the coolant that allows giant molecular clouds to collapse and form new stars. Without dust, gas in a galaxy stays hot, it stays diffuse, it resists gravity. Star formation is sluggish, inefficient and stunted. With dust, gas cools rapidly, it clumps, it fragments, it collapses into the dense cores that ignite into new suns. Dust is the governor of the galactic engine. It controls the pace of star formation, and if the early universe was rich in dust because of Wolf-Rayet stars like WR124, then the first galaxies did not form stars slowly and hesitantly. They formed stars in a furious explosive burst. They were hyperactive. They were breeding grounds for stars at a rate that dwarfed anything we see in the modern universe. The very existence of the galaxies we see at high redshift, the ones that baffled us with their maturity and their complexity, is explained by the dust that Webb has now observed being manufactured in real time. There is another layer to this story, a layer that touches on the search for life itself. The dust around WR124 is not just any dust. It is carbon-rich. It contains the full spectrum of organic chemistry, and the manner in which that dust is expelled, in massive, clumpy, turbulent outflows, is critical. It is not a gentle, uniform mist. It is a violent, chaotic eruption. That turbulence is essential. It mixes the dust with the surrounding interstellar medium. It stirs the pot. It ensures that the organic molecules are not confined to a small, sterile bubble around the dying star. They are scattered across vast volumes of space. They are injected into the galactic ecosystem. They become part of the raw material from which new stars and new planetary systems will form. The turbulence of stellar death is the mixing bowl of life. Consider the alternative. If dust were produced only in the quiet, gentle outflows of red giants, it would be more locally confined. It would be enriched in certain regions but absent in others. The chemical heterogeneity of the galaxy would be extreme. Some stellar nurseries would be rich in the building blocks of life. Others would be barren. The probability of life emerging on any given planet would be a roll of the cosmic dice, heavily dependent on its location in the galaxy. But Wolf-Rayet stars, with their violent, wide-ranging ejecta, homogenize the galaxy. They spread the organic wealth. They ensure that the chemical ingredients for life are not a rare luxury, but a common commodity. They democratize the potential for biology. This is a profound shift in perspective. We used to think of the universe as a place where life was possible only in special, privileged pockets. We thought of the galactic habitable zone, a narrow ring around the center of the galaxy, where the metallicity was just right and the radiation environment was not too harsh. We assumed that most of the galaxy was sterile. WR124 forces us to reconsider. It suggests that the galaxy is far more chemically uniform than we imagined, that the building blocks of life are pervasive, that the potential for biology exists in far more places than we dared to hope. The number of potentially habitable planets in the Milky Way may be orders of magnitude larger than our old estimates. And this is where the historical context becomes crucial. Think back to the Copernican revolution. We learn that Earth is not the centre of the universe. Then we learn that the Sun is not the centre of the universe. Then we learn that the Milky Way is not the only galaxy. Each step was a demotion. Each step made us feel smaller, more insignificant, more alone. The discovery of WR1124's dust production and its implications for the early universe is a different kind of revolution. It is not a demotion, it is an elevation. It does not make us smaller, it makes the universe larger, richer, more thickened. It suggests that the conditions that gave rise to life on Earth are not a bizarre fluke. They are a cosmic norm. The lonely, fragile island of life in a dead universe narrative is giving way to a narrative of a universe that is teeming, chemically, with the potential for life. We are not special because we are rare. We are special because we are the conscious expression of a common cosmic process. And that brings us back to the star itself. WR124. It is a monster. It is 30 times more massive than the Sun. It burns through its nuclear fuel at a ferocious rate. It is doomed to a short, spectacular life. It will end its days not with a whimper, but with a bang, a supernova, a cataclysm that will outshine 1 billion suns. And in that final, shattering moment, the dust that it has been painstakingly manufacturing for the last few 100,000 years will be blasted outward at a significant fraction of the speed of light. The organic molecules will survive that shock. They are resilient. They will be scattered across hundreds of light years of space. They will seed the galaxy. They will enrich the next generation of stars and planets. The death of WR124 will be one of the most energetic events in the galaxy. It will be visible from across the observable universe. And when it happens, the Webb telescope or its successors will be watching. They will trace the expanding shockwave. They will map the distribution of the newly synthesized elements and molecules. They will witness the final explosive act of this cosmic dust factory. And that data will be the final piece of the puzzle. It will confirm everything we have inferred from the quiescent dust production we see today. It will complete the picture of how the elements of life are born, live and die, and are reborn again. We are living through a golden age of discovery. The James Webb Space Telescope is not just a machine. It is a time machine. It is a chemical analyzer. It is a window into the soul of the universe. And what it has shown us, through the lens of a single dying star, is that the universe is not a cold, indifferent place. It is a place of incredible, violent, beautiful creativity. It is a place that builds complexity. It is a place that, given time and the right conditions, generates beings that can look back and understand their own origins. The dust you breathe today, the carbon in your cells, the oxygen in your lungs, the calcium in your bones. Every atom heavier than hydrogen was forged in a star, but the James Webb Space Telescope has now shown us that the story is more intimate than that. The atoms were not just forged, they were assembled. They were organized. They were packaged into complex molecules. The star died so that you could live. That is not poetry. That is physics. That is chemistry. That is the data. And so, when you look at the image of WR124, that delicate, glowing, ethereal nebula, do not see just a beautiful picture. See a factory. See a testament to the relentless drive of the universe towards complexity. See a story that began 15,000 years ago with a photon of light, that travelled across the galaxy, that entered the mirror of a telescope built by the children of stardust, and that revealed the machinery of creation itself. The impossible discovery is inside a dying star is the most hopeful story we have ever told about ourselves. It is the story of how the universe, through the violence of stellar death, creates the quiet, patient conditions for life. It is the story of how the universe learns to see itself. And so we come to the inescapable conclusion. The star we've been watching, the one that gave us that impossible discovery, is heading for a violent end. Wolf-Rayet 124, or WR124 as astronomers call it, is a ticking time bomb. And I mean that in the most literal, mind-blowing sense. It is a dying star, yes, but it isn't just fading away like a candle sputtering out. No, this thing is going to go out with a bang, absolutely the biggest bang you can imagine. It is destined for a core collapse supernova. Now, let's sit with that for a second. When I say core collapse, what I'm talking about is the very heart of the star suddenly giving way. You see, for millions of years, WR124 has been fighting gravity. Every second of its life, it has been engaged in this cosmic tug of war. The immense pressure and heat in its core have been fusing lighter elements into heavier ones, releasing energy that pushes outward. That outward push is what keeps the star from collapsing under its own enormous weight. But eventually, the fuel runs out. The core, now made mostly of iron, can't fuse into anything else without consuming energy instead of releasing it. So the pressure drops. And gravity, the ultimate winner in this fight, wins in an instant. The core collapses. And I mean collapses. In less than 1 second, a sphere of iron roughly the size of Earth, but containing more mass than our entire Sun, implodes down to the size of a city. The math behind this is terrifyingly beautiful. In that single heartbeat, the energy released is greater than everything our Sun has produced in its entire 10 billion year lifetime. 10 billion years of gentle, steady sunshine, all packed into a blink of an eye. That is the power of a supernova. That shock wave, travelling at roughly 30,000 kilometers per second, will absolutely rip through the surrounding space. But here's where it gets visually stunning. Remember that beautiful nebula we talked about earlier, the one called M167? That swirling cloud of gas and dust that WR124 has been shedding for tens of thousands of years? Well, when that shockwave hits it, it's going to light it up like a Christmas tree. The nebula will be illuminated from the inside out, creating a supernova remnant that will be visible across half the universe. For a few weeks, this explosion will outshine every other star in its galaxy. It will be a beacon of raw cosmic violence. But, and this is the part that really gets me, the story doesn't end with destruction. It never does it? In the aftermath of that blast, the dust we've been talking about, the stuff that James Webb just found, faces two very different fates. A lot of it will be vaporized. The intense radiation and the sheer force of the shockwave will rip those fragile grains apart, turning them back into individual atoms. On the surface, that sounds like a tragedy. We found this incredible cosmic ingredient for planets, and then it gets completely destroyed. But not all of it. Some of that dust, maybe even most of it, will survive. It will be protected, ironically, by the very density that makes it so fascinating. The shockwave might compress the dust grains, even shatter some of the bigger ones into smaller pieces, but it won't annihilate them. This surviving dust is then injected into the interstellar medium, the vast, cold space between the stars. And here's where the connection to us, right here on Earth, becomes undeniable. That surviving dust, forged in the winds of a dying star and hardened by the blast of a supernova, becomes part of the galactic dust budget. Think of it like a cosmic bank account of raw materials. Every star that explodes makes a deposit. Every new star that forms makes a withdrawal. And the James Webb Space Telescope just showed us that stars like WR124 are making much bigger deposits than we thought. They are the heavy hitters in this economy. Some of that dust will just drift in space for billions of years, but some of it will get very lucky. It will find itself in a giant molecular cloud, a region of space where gravity is starting to pull gas and dust together. As that cloud collapses, it spins, flattening out into a disk, and within that disk the dust starts to clump. It sticks together, grain by grain, forming pebbles, then boulders, then planetesimals, and eventually whole planets. The iron in Earth's core? It came from a star like this. The calcium in your bones? A star like this. The oxygen you're breathing right now? Absolutely. The dust from WR124, or a star just like it, is already part of you. So when WR124 finally explodes, it won't just be an ending, it will be a beginning for countless new star systems. And some of those systems, given the right conditions, might foster life. They might host planets with oceans and atmospheres. They might host creatures that look up at the night sky and wonder where they came from. And the answer will be the same. They came from the dust of 1,000,000 dying stars. But there is another, more frightening possibility. It all depends on just how massive WR1T4 really is. If it tips over a certain threshold, it might not just go supernova. It might produce something far more terrifying, a gamma ray burst. These are the most energetic events in the universe since the Big Bang. Imagine focusing the entire energy output of a supernova into a narrow beam, a laser beam of pure death that could sterilize half a galaxy. If WR124 is massive enough, its core might collapse directly into a black hole, and in doing so, it might fire off one of these cosmic death rays. For now, astronomers think it's unlikely, but the possibility is there, lurking in the data. After the explosion, what's left? That depends entirely on the mass. If WR124 is on the lower end of the Wolf-Rayet scale, the core that doesn't get blown away will collapse into a neutron star. A city-sized object spinning hundreds of times a second with a magnetic field so strong it would rip the atoms right out of your body from 1,000 miles away. If it's on the higher end, that core will keep collapsing past the point of no return, and become a black hole, a singularity, a point in space where gravity is so strong that not even light can escape. And given what we've just learned about its dust, and therefore its mass loss, the odds are leaning towards that second option. Now, when is this all going to happen? On human timescales, it feels like waiting for a bus that's never coming. Astronomers estimate that WR124 will explode within the next few 100,000 years. That sounds like an eternity to us. An entire human civilization could rise and fall 1,000 times over in that span. But in astronomical terms, a few 100,000 years is nothing. It's the blink of a cosmic eye. WR124 is already in its death throes. It is, for all intents and purposes, a corpse that hasn't hit the ground yet. It is the most imminent explosion of its kind that we know of. This is where the James Webb Space Telescope has completely rewritten the textbooks. Before Webb, our models of stellar evolution, the life stories of stars, were based on a lot of guesswork. We knew stars lost mass, but we had no idea how much dust they were actually making. We had theories, but we couldn't see the details. Webb's infrared eyes pierced through the glowing gas and saw the dust grains themselves. It measured their size, their composition, and their quantity, and the results were shocking. The mass loss rates for stars like WR124 are significantly higher than we predicted. This is a huge deal. If these stars are losing more mass than we thought, it changes everything. It changes our predictions for exactly when they will explode. It changes the mass of the core they leave behind. And that directly feeds into our predictions for black hole formation. If we underestimate the mass loss, we think the star will leave behind a lighter black hole. If we account for the real dust, we get a heavier black hole, and heavier black holes have different merger rates. This is the link to gravitational wave observatories like LIGO. You've probably heard of LIGO, the instrument that detects ripples in spacetime itself, or when two black holes collide. Those collisions are the most violent events in the universe, sending out vibrations that literally stretch and squeeze our planet by a fraction of the width of an atom. Before Webb, our models for how many of these collisions should happen were all over the place. We didn't know how many massive stars were turning into black holes. We didn't know how heavy those black holes were. Now we do. The dust measurements from WR124 are like a Rosetta Stone for black hole demographics. By understanding exactly how much material this star is losing, we can calculate the exact mass of the core that will collapse. And that tells us the starting mass of the black hole it will become. This feeds directly into population models that predict how often these black holes should find each other, spiral in and merge. Webb is essentially helping us calibrate the entire cosmic census of black holes. It is connecting the smallest particles, the dust grains, to the largest structures, the gravitational waves that shake the universe. So, what does this all mean? It means that we are living through a revolution in astrophysics. The James Webb Space Telescope isn't just taking pretty pictures. It is providing the hard data that forces us to rip up our old theories and start over. The discovery inside WR124 has sent shockwaves through the scientific community, and I mean that literally. The dust we found is rewriting the story of how stars live, how they die, and what they leave behind. We've gone from seeing a dying star to understanding its entire cosmic legacy. We see the dust that will build future worlds. We see the core that will become a black hole. We see the explosion that will light up a galaxy. And we see the connection between that explosion and the very fabric of space-time itself. It's all connected. It's a chain of events that stretches from the quantum realm of dust grains to the cosmic scales of gravitational waves. And as we wait for WR124 to finally meet its end, we can be confident in one thing. When it does, we will be watching. The telescopes will be pointed. The theorists will have their models ready. And the James Webb Space Telescope, the same instrument that made this impossible discovery, will be there to capture the afterglow. It will see the birth of a supernova remnant. It will trace the surviving dust as it spreads into the galaxy. And it will give us the final chapter of a story that began millions of years ago in the heart of a dying star. The coming supernova is not just a spectacular display of cosmic fireworks. It is a key that unlocks the secrets of stellar evolution. It is a confirmation that the universe is a recycling engine, constantly breaking down the old to build the new. And it is a reminder that we, the audience of this cosmic drama, are not just passive observers. We are made of the same stardust. We are the direct descendants of every supernova that has ever happened. The death of WR124 will be the most hopeful, the most beautiful, and the most violent thing we will never see up close. But thanks to the impossible discovery we just made, we will understand it better than we ever have before. When that image of WR124 hit the internet, nobody was prepared for what happened next. NASA posted it, and within hours, it wasn't just breaking records, it was shattering them. By the end of 2023, that single picture of a dying star, surrounded by an ethereal, golden halo of cosmic dust, became the most downloaded scientific image of the entire year. Think about that for a second. We live in a world where cat videos, celebrity selfies, and political memes dominate the internet, and yet, a photograph of a star over 15,000 light-years away, a star that is literally tearing itself apart, was the one thing people couldn't stop looking at. Tens of millions of views. Not because it was cute, not because it was funny, but because it was real. It was raw, and it was something our eyes had never seen before. The global response wasn't just from the public, though. That image shook the scientific community to its core. Within weeks, the biggest names in astrophysics were scrambling to get their hands on the raw data. The Massachusetts Institute of Technology, the European Southern Observatory, the Space Telescope Science Institute. Everyone wanted a piece of the action. But here's the thing that really tells you how big this was. The International Astronomical Union, the same body that decides what gets to call itself a planet, formed a dedicated Wolf-Rayet dust working group. Not a subcommittee, not a side project. A full-blown working group populated by the sharpest minds on the planet, all focused on one single question. What the hell is happening inside Wolf-Rayet stars? And how does the dust they produce survive long enough to seed the universe? That group didn't just meet once. They started holding regular conferences, sharing data in real time, and building a collective understanding of something we barely understood a decade ago. And the collaboration didn't stop at the astronomers. This discovery forced disciplines that rarely talk to each other to sit down at the same table. You had dust physicists, people who spend their entire careers studying how microscopic grains of silica and carbon clump together in interstellar space, suddenly in the same room as stellar wind dynamicists who model how plasma explodes from the surface of a star at millions of miles per hour. And then you had the binary star experts, Because it turns out that most massive stars aren't lonely. They dance with a partner, and that dance can change everything. These three groups started meeting in person, sharing slide decks, and arguing over coffee about whether the dust forms in the shockwave of the stellar wind or in the cool shadow of a companion star. That kind of cross-disciplinary firestorm is rare. It's messy, it's human, and it's exactly the kind of chaos that produces real breakthroughs. But here's where it gets really personal. Graduate students, the ones who are literally building their futures on this work, saw the WR-124 data and realized they had stumbled onto a goldmine. Within months, dissertations were being drafted. Whole PhD projects were rewritten overnight. One student at the University of Arizona told me their advisor basically threw a folder on their desk and said, "Forget your previous project, you're working on this now." And that's the thing about a discovery like this. It doesn't just rewrite textbooks, it rewrites careers. These young scientists are now the ones who will carry the torch. They're analysing the spectral lines, mapping the dust grains, and running simulations that try to explain how a star can shed so much of its mass and still keep burning. And because NASA and ESA made the data publicly available after exactly 12 months, anyone in the world with an internet connection and enough patience could download the same dataset. No gatekeeping, no secret archives. The raw, unprocessed truth of that dying star sat on a public server for anyone to use. That is the kind of transparency that makes science beautiful. The ground-based response was equally impressive. You can't just look at a star like WR-124 with one telescope and call it a day. You need every wavelength. You need the whole picture. So astronomers coordinated time on the largest telescopes across the planet. In Chile, the Very Large Telescope pointed its massive mirrors at the star, capturing its infrared glow. In Japan, the Subaru telescope took a crack at it, adding optical data that revealed details Webb couldn't see. In Germany, the Effelsberg radio telescope listened for the faint hiss of stellar wind, interacting with the interstellar medium. And in India, the giant Metrowave radio telescope picked up the low-frequency radio emissions that come from the most energetic particles being flung out into space. This wasn't a solo act. It was a symphony. Dozens of observatories, hundreds of scientists, all pointing their instruments at the same spot in the sky, trying to piece together a story that started millions of years ago and will end in a flash of light we will never see. And because of this coordinated effort, the impact rippled far beyond just one star. The proposals for the next generation of space observatories started to shift. Engineers who were designing the successors to Hubble and Webb began incorporating lessons learned from WR-124. They realized that future telescopes need better mid-infrared spectrographs. They need higher resolution images that can resolve the fine structure of dust shells. They need instruments that can handle the extreme brightness of a Wolf-Rayet star without saturating the detectors. The impossible discovery we made inside that dying star didn't just change what we know. It changed what we want to know next, and it changed the tools we're building to go find it. But WR-124 wasn't the only dying star Webb had its eye on. The telescope has been scanning the graveyards of the cosmos with a relentless curiosity. Take the Crab Nebula, for example. That's the remnant of a supernova that Chinese astronomers saw explode in the year 1054. Webb looked at it and found something nobody had seen before. Inside the tangled mess of filaments and gas, Webb revealed a sort of skeleton of the explosion, a lattice of pristine, ionized material that seemed to be holding the entire nebula together. It was like seeing the bones of a dead star for the first time. And those filaments aren't just pretty. They're teaching us how magnetic fields shape the debris of an explosion, how the shockwave from the original blast is still ripping through space, almost 1,000 years later. Then there's the Ring Nebula. You've probably seen the pictures, that beautiful, eye-shaped cloud of gas that looks like a cosmic smoke ring. But Webb's infrared eyes cut through the dust and revealed something far more complex. Instead of a simple ring, we saw concentric shells, like the layers of an onion, each one representing a pulse of mass loss from the central star. And at the very centre, lurking in the glare, Webb found evidence of a companion star, a hidden binary. That tiny faint star is probably the one that stirred the pot, that triggered the mass loss that created those perfect rings. It's a dance of death, and we were only watching one partner before. And then there's Cassiopeia A, the youngest known supernova remnant in our galaxy. The explosion happened about 350 years ago, but the light only reached Earth around the year 1670. Webb went into that cloud of chaos and found a chemical complexity that blew our minds. You name an element, it's probably in there. Silicates, sulfur, argon, neon, iron. Pieces of a star that are now floating through space, waiting to be recycled into new planets, new life, new everything. It's a library of stellar chemistry, and Webb is the first telescope that can read every page. The image of Cassiopeia A is so dense with information that scientists are still unravelling it, layer by layer, like peeling back the pages of a book written in fire. And of course, the Southern Ring Nebula. This one was already famous, but Webb's image revealed something astonishing. That seemingly simple cloud of gas is actually hiding a binary star at its heart. Two stars orbiting each other in a tight embrace, one of them dying and the other still burning bright. The dying star has been ejecting shells of gas for thousands of years, but the companion star has been shaping those shells, bending them, twisting them, creating a structure that looks almost like a cosmic hourglass. Webb's mid-infrared instrument caught the glow of that companion star, proving once and for all that the Southern Ring is not a solo act. It's a duet, and the music is the slow, beautiful, tragic dispersal of a star's body into the void. So where does all of this leave us? We are living in what I genuinely believe is the golden age of stellar astrophysics. It's not just that we have better telescopes, it's that we have the right telescope at the right time. Webb is not just taking pretty pictures, it's building a unified theory of stellar death. Every dying star it observes adds another piece to the puzzle. WR124 showed us how dust is born. The Crab Nebula showed us how explosions sculpt the interstellar medium. The Ring Nebula showed us how binary companions can shape a star's final moments. Cassiopeia A showed us the chemical inventory of a dead star. The Southern Ring Nebula showed us that we've been underestimating the role of hidden companions. Taken together, these observations are painting a picture that no one had ever seen before. A picture of how stars end their lives, how they seed the universe with the elements that will one day become planets, oceans, and people. And that unified theory is exactly what we need, because for decades we've had fragments. We knew that massive stars explode. We knew that low-mass stars puff off their outer layers, but we didn't know the full story. We didn't know why some stars produce more dust than others. We didn't know how binary companions affect the process. We didn't know how the magnetic fields of a dying star can channel its outflow into jets and rings. Webb is changing all of that. Every observation is a data point. Every image is a chapter, and we are only at the beginning. The impossible discovery we made inside WR124 was just the first page. The rest of the book is being written right now, in real time, by scientists all over the world who are looking at these images and asking the one question that drives all of science. What happens next? What happens next that we must reconcile Webb's observations with the old theories? And it is a brutal process. The textbooks that sit in university libraries, the ones written in the 90s and early 2000s, they describe stellar evolution as a relatively clean sequence. A star burns hydrogen, then helium, then carbon, and then, depending on its mass, it either puffs off a planetary nebula or goes supernova. But Webb has thrown a wrench into that clean narrative. The observations of WR124 show that the star is shedding mass at a rate that is almost absurd. It is losing the equivalent of the Earth's mass every few months. That is not in the textbooks. The models predicted that Wolf-Rayet stars had powerful winds, but they did not predict the sheer volume of dust that Webb is seeing. The dust is not a thin haze, it is a dense, structured shell that is blocking a significant portion of the star's light. That means the star is losing mass faster than we ever calculated. And if that is true, then the lifetimes we have assigned to these stars, The timelines we use to understand the evolution of galaxies, they are all off. This has forced a reckoning in the field of stellar nucleosynthesis. For decades, we believed that the heavy elements, the carbon and oxygen and iron that make up our bodies, were primarily cooked in the cores of massive stars and then scattered by supernovae. That is still true, for the most part, but Webb is showing that Wolf-Rayet stars like WR124 are doing something else. They are not just cooking elements in their cores, they are actively manufacturing dust in their outer atmospheres, and that dust is not simple soot. Webb's spectrographs have detected the signatures of silicates, of alumina, of complex carbon compounds. These are the raw ingredients of rocky planets. The implication is staggering. A significant fraction of the raw material that built Earth, that built Mars, that built every asteroid in the asteroid belt, did not come from supernovae alone. It came from the quiet, steady, relentless wind of stars like WR124, stars that are hemorrhaging their bodies into space long before they finally explode. The universe has been seeding itself with the stuff of life for billions of years, and we are only now seeing the factory. To understand the full impact of this, you have to appreciate where we were just 20 years ago. Before the launch of the Spitzer Space Telescope, our view of cosmic dust was pathetic. We could see it as a vague infrared glow, but we could not resolve its structure. We knew dust existed because it dimmed the light of distant stars, but we had no idea how it was made. The leading theory was that dust formed in the cool, dense atmospheres of red giant stars, and that was the end of the story. Then, in the early 2000s, Spitzer began to find dust in places it had no business being, like around supernovae and around hot, massive stars. That was the first crack in the old theory. But Spitzer was limited. Its resolution was good, but it could not see the fine details. It was like trying to read a book from across the room. You know there are words, but you cannot make out the letters. Webb is different. Webb is holding the book right in front of our faces. And what we are reading is a story that is far more complex than anyone imagined. The historical context here is crucial. The concept of stellar death has haunted human imagination since we first looked up at the sky. The ancient Greeks believed that stars were eternal fires. The Babylonians thought they were gods. It was not until the 16th century, when Tycho Brahe observed a supernova in 1572, that we began to understand that stars could change, that they could even vanish. But it took another 400 years for us to understand the mechanism. In the early 20th century, the work of Cecilia Payne-Gaposchkin and others gave us the tools to read the chemical composition of stars. In the 1960s, the discovery of neutron stars and black holes gave us the endpoints of stellar evolution. But the middle part of the story, the part where the star actually transitions from a stable burning object into a corpse, that remained a dark room we could not enter. We knew the door was there, but we did not have the key. Webb is that key. The key turned when the JWST Mid-Infrared Instrument, or MIRI, locked onto WR124. MIRI operates at wavelengths between 5 and 28 microns. That is the sweet spot for seeing cool dust. And when the data started flowing, the scientists at the Space Telescope Science Institute saw something that made them stop. The dust shell was not smooth. It was clumpy. It was filamentary. It looked like a cotton candy nebula, but with structure that suggested turbulence and magnetic fields and shock waves. The clumps are not random. They are organized into arcs and bubbles, as if the star's wind is being shaped by forces we cannot see. The leading hypothesis is that the star's magnetic field, which we assumed was weak in Wolf-Rayet stars, is actually strong enough to pinch and channel the outflow. If that is true, it changes everything. Magnetic fields are the invisible hands that shape so much of the universe, from sunspots to galaxy clusters. Finding that they are active in the final death throes of a massive star means we have to add a new variable to every model of stellar evolution. The implications for exoplanet research are equally profound. If dust is being produced by Wolf-Rayet stars in such massive quantities, then the interstellar medium is richer in solid material than we thought. That means the process of planet formation is more efficient. It means that the disks of dust and gas around young stars, the ones that give birth to planets, are being replenished by older, dying stars. The universe is not a static place where matter is created once and then slowly degrades. It is a dynamic recycling ecosystem. The death of one star is the birth of another's planetary system, and Webb is giving us the raw data to quantify that cycle. We can now calculate with reasonable accuracy how much dust a single Wolf-Rayet star contributes to the galaxy over its lifetime, and the numbers are enormous. Hundreds of Earth masses of dust per star. Multiply that by the millions of Wolf-Rayet stars in the Milky Way, and you realize that the galaxy is raining dust. It is a silent, continuous downpour of solid matter that has been going on for billions of years. But the most profound impact of the WR-124 observation may be yet to come. It has triggered a wave of proposals to target every known Wolf-Rayet star in the Milky Way. The James Webb Space Telescope's time is the most precious resource in astronomy. Every minute of observation is fought over by thousands of scientists. After the WR-124 image was released, the next call for proposals saw a flood of applications to study Wolf-Rayet stars. The committee had to allocate hundreds of hours of telescope time to this one class of object. Over the next 2 years, Webb will examine a sample of dozens of Wolf-Rayet stars of different masses, different temperatures, different stages of evolution. The goal is to build a comprehensive catalogue. We want to know how the dust production scales with mass. We want to know if binary companions are necessary for the most dramatic structures. We want to know if the dust chemistry changes over the lifetime of the star. This is not just a single discovery. It is the opening of a whole new chapter of astrophysics, and it is not just about the stars themselves. The dust that WR-124 is throwing into space will eventually cross the galaxy. Some of it will end up in molecular clouds, the nurseries where new stars and new planets are born. That means the carbon and silicon and oxygen that once belonged to a star 15,000 light-years away will one day be part of a new world. Perhaps a world with oceans, perhaps a world with life. We cannot follow that dust across the galaxy, not yet. But we can model it. We can track its trajectory using simulations, and we can measure its composition with such precision that we will know exactly what elements are being delivered to the next generation of stars. We are witnessing the slow, majestic circulation of cosmic matter. The response to this has been a renaissance in the study of stellar winds. For years, stellar winds were considered a niche topic, something that mattered for understanding mass loss, but was not central to the big questions. That has changed. Conferences on stellar winds, which used to draw a few dozen specialists, are now overcrowded. Graduate students who used to study galaxy formation are pivoting to study the physics of dust nucleation. Theorists who spent their careers modelling supernovae are now trying to understand the gradual, constant loss of mass from Wolf-Rayet stars. The field is being reshaped, and it is being reshaped by a single image. The image of WR-124 is not just a scientific artifact. It is a cultural artifact. It has appeared on magazine covers, in art galleries, in music videos. People who do not know the difference between a red giant and a white dwarf have this image burned into their memory. And that matters. When the public is captivated by science, it creates pressure on governments and funding agencies to keep investing. The James Webb Space Telescope cost $10 billion. There were politicians who called it a boondoggle, but now, when those same politicians see the image of WR-124, when they see the public reaction, they cannot argue. The return on investment is not just data. It is inspiration. It is a reminder that we are part of something larger. It is a reminder that the universe is beautiful and it is worth understanding. The work continues. Every day, new data is being processed. New papers are being written. The working group on Wolf-Rayet stars is planning a massive survey, and somewhere in a dusty archive of the Space Telescope Science Institute, the raw data on WR-124 sits, waiting for the next person to download it. Maybe it will be a professional astronomer. Maybe it will be an amateur. But whoever opens that file will be seeing the ghost of a ghost that is still shining, a star that is still dying, a star that is still giving its body to the universe. And that is the legacy of this discovery. It is not just a moment, it is a beginning. And so, we find ourselves standing at the precipice of a single dying star, looking at a ghost that is still shining. But what, exactly, is that ghost made of? What chemical secrets has it been keeping, locked inside its fading light for millions of years? The answer is not just a scientific curiosity. It is the story of our own potential origins, written in the dust of a star that is giving its all to the universe. The chemistry is, in a word, staggering. When the James Webb Space Telescope turned its golden eye toward this stellar cadaver, it didn't just see gas and heat. It saw a cosmos of molecules. It found carbon-based grains, the kind of stuff that you and I are made of, the backbone of life itself. It found polycyclic aromatic hydrocarbons, or PHs. Now say that 5 times fast. Polycyclic aromatic hydrocarbon. They sound like something out of a chemistry textbook that you'd skim past on the way to the fun chapters. But here's the thing. PAHs are these complex, ring-shaped organic molecules floating around in space. On Earth, they form when you burn something, like a campfire or a car engine. But in space, they are the fundamental building blocks for more complex organics, the precursors to the ingredients of life. Finding them in a dying star is like finding a chef's recipe book inside a volcano. It doesn't seem like it should be there, and yet there it is. And the PAHs are just the appetizer. The Webb telescope also identified silicate grains. Now silicates might sound boring. They're just rock, right? Just sand, dust, but hold on. These aren't just any silicates. These are the same kinds of minerals that form the rocky crust of Earth. We're talking about olivine and pyroxene. Olivine is that green, gem-like mineral you might have seen in volcanic rocks. Pyroxene is the dark, dense stuff that makes up the mantle of our planet. Webb found these minerals in staggering detail inside the outflow of this dying star. And here's where it gets really interesting. The grains vary enormously in size. Some are just a few nanometers across, 100,000 times smaller than the width of a human hair. Others are big, reaching up to a few microns. Size matters in space. The tiny grains behave like smoke. They float around, scattering light. The larger grains sink and clump together. That clumping is the first step toward building a planet. There's a difference too in their structure. Some of these grains are amorphous, meaning their atoms are jumbled up like a chaotic pile of bricks. Others are crystalline, where the atoms are lined up in perfect ordered rows, like a meticulously built wall. Finding crystalline olivine in a dying star is a big deal. It tells us that the environment inside that stellar explosion is not a wild, random mess. It is a place of structure, of order. It is a chemical factory running at full capacity, producing the raw materials for future worlds. Every single grain of dust that Webb detected is a tiny piece of a future planet, a future Earth, a future you. Think about that for a second. The carbon in your bones, the oxygen you breathe, the iron in your blood, it all came from stars that lived and died long before our sun was even a thought. But this discovery gives us a direct, front-row seat to the process. We are watching a star actively manufacturing the ingredients for a solar system. We are seeing the chemical assembly line. And if you want to get poetic about it, we are watching the universe prepare a nursery. When that nursery is ready, when the dust clouds collapse and compress, new planets will form. And those planets will inherit this exact chemistry. They will inherit the PAHs, the silicates, the olivine, the pyroxene. They will inherit the legacy of a star that died so that they could live. Now, how did we get here? How do we go from staring at a faint point of light in the night sky to knowing the exact atomic composition of a dying star's innards? That is a story of human perseverance, a saga spanning 156 years. It starts in 1867 with 2 men, Charles Wolf and Wolf-Rayet. They were working at the Paris Observatory, and they were doing something very simple. They were looking at the spectra of stars, splitting their light into a rainbow of colours. Just a simple prism, and in the light of certain faint stars, they saw something strange. Instead of a smooth rainbow, they saw bright glowing lines like neon signs. These lines were the signature of hot, energetic gas. They call these objects Wolf-Rayet stars. They had no idea what they were looking at. They just knew these stars were different. They weren't like the sun. They were something wilder. For decades that mystery lingered. The lines were just a puzzle. They didn't have the physics to explain them. That explanation had to wait for the birth of quantum mechanics. In the early 20th century, physicists like Niels Bohr and Max Planck figured out that atoms absorb and emit light at very specific wavelengths. Those bright lines that Wolf and Rayet saw, they were the fingerprint of atoms jumping between energy levels. Suddenly, the cryptic light show made sense. Those lines were telling us about the temperature, the density, and the chemical composition of the star. It was a revolution. We could read the stars' stories. But still, we were stuck. We could only see the visible light. And a lot of the action was happening in the infrared, the part of the spectrum we can't see with our eyes. So we waited. We built new eyes. The first serious infrared observations of these stars happened in the 1980s. They were crude by modern standards, just a few pixels on a detector. But they showed us that these stars were surrounded by massive clouds of warm dust. The dust was glowing. We were starting to see the ghost. Then came the Hubble Space Telescope. Hubble looked at the same region in visible and ultraviolet light. It showed us the structure. It showed us the shock waves, the arcs, the clumps of gas moving at millions of kilometers per hour. We could finally see the shape of the ghost, but Hubble couldn't see the dust itself. It was like seeing the wind by looking at the trees, but not seeing the wind itself. So we launched the Infrared Space Observatory, ISO, and then the Spitzer Space Telescope. These missions gave us our first real maps of the dust, the silicates, and the organic molecules. They filled in some of the blanks, but they were low resolution. They were like looking at a masterpiece painting through a frosted glass window. And that brings us to Webb. The James Webb Space Telescope is the culmination of 156 years of science. It is the grandchild of Wolf and Rayet's prism. It is the fruit of the labours of thousands of engineers, scientists, and dreamers. It is the most powerful infrared telescope ever built, and it was designed specifically for this moment. To look at the dust, to dissect the chemistry, to see the ghost in its full, terrifying, beautiful glory. Every single piece of knowledge from the past century and a half led to this single observation. It is a legacy of curiosity, a monument to human ingenuity. And that brings us to the human beings behind the machine. Because a telescope, no matter how powerful, is just a collection of mirrors and electronics. It is the people that give it a soul. The lead scientist on this project is a woman named Erin Wheatley. When the first data streamed down from Webb and the images appeared on her screen, she didn't say anything scientific. She didn't start writing a paper, she cried. She broke down. She looked at the swirling chaos of a dying star, and she saw the work of her entire career, the hopes of her colleagues, the investment of an entire agency, all distilled into a single beautiful image. She saw the ghost, and she wept. That is a human reaction. That is the price of obsession. She wasn't alone. She leads an international team spanning 12 countries. Astronomers in Germany, France, the United Kingdom, Japan, Australia, Canada, the United States. They all contributed. They all argued. They all stayed up late, staring at data, questioning each other, pushing each other. And before any of them could see that data, they had to endure something brutal. A proposal review. The James Webb Space Telescope is so oversubscribed that only a tiny fraction of proposals are accepted. For every hour of observing time, there are 10 hours of requests. This team had to write a compelling case, a story, a justification. They had to convince a panel of their peers that this dying star was worth the time of the most expensive telescope ever built. The review process took 2 years. 2 years of waiting, of wondering, of hoping. They got the time, they got the gold. But the first people to lay eyes on that raw data were not the senior scientists. They were graduate students, young men and women, barely out of college, sitting in front of computer terminals, running the calibration pipelines. They were the first human beings in history to see the ghost. Can you imagine that moment? You're a student, you're tired, you're running a script, and suddenly the graphic appears. and you realize you are the first person in 4 billion years of Earth's history to see the chemical death of a distant sun. That is a moment that changes a person. And it didn't stop with the professionals. Amateur astronomers around the world contributed archival data. They had been tracking this star for years, using backyard telescopes, monitoring its brightness, measuring its changes. Their data helped pinpoint the most interesting moments, the flares, the pulses. They were the scouts. The professionals took over for the final assault, and then the artists got involved. Science communicators, graphic designers, visualization experts. They took the raw invisible infrared data and translated it into human vision. They painted the colours, they defined the shapes, they made the ghost visible to everyone. Their work proliferated across the internet, across news channels, across social media. It turned a scientific paper into a global phenomenon. And let's not forget the citizen scientists. The people who didn't have a PhD, who didn't have a telescope, but who had a curious mind. They joined online platforms where they could help classify the grains, measure the dust, spot the anomalies. They were the army, the crowd. They contributed real meaningful labour to this discovery. It was a reminder that science is not a closed club. It is a conversation, an open invitation, and that invitation is still open, because this is not the end. This is a beginning. The data from Webb is still being analysed. More papers will be published. More students will find their vocations. More amateur astronomers will point their telescopes at the same spot. More science communicators will make videos. More artists will find inspiration. The ghost of that dying star will continue to shine, not just in the sky, but in our minds. It will fuel a generation of astronomers. It will be a touchstone for decades. And one day, someone, somewhere, will look at a new image from a future telescope, and they will remember this moment. They will remember that it all started with a prism in a Paris observatory, a few quantum leaps, and a woman who cried when she saw a ghost. And they will be grateful. So should we. B-roll, close-up of a prism refracting light, transitioning to an animation of atoms emitting spectral lines. Then, a montage of telescopes, Hubble, Spitzer, and finally Webb deploying in space. End with a slow zoom into a swirling nebula, with grains of dust forming in the foreground. Think about that for a moment. Every single carbon atom in your body, everyone in the tree outside your window, everyone in the diamond on a ring or the graphite in a pencil, was forged in the heart of a star that lived and died long before our sun ever ignited. That is not a poetic metaphor. That is physics. That is the cold, hard, beautiful truth of our existence. We are not just born from stardust. We are stardust that has woken up, looked around, and started asking questions. And for that to happen, the universe had to be brutal. It had to be violent. Stars had to burn, and they had to die. Stellar death is not an ending. It is the mechanism of cosmic complexity. It is the universe's way of recycling its most precious materials, of ensuring that the hydrogen and helium of the Big Bang eventually became the calcium in our bones and the oxygen in our lungs. So what does that mean for a star like WR124? It means its death is not a waste. It is not a tragedy. It is a gift. When that Wolf-Rayet star finally collapses, when it explodes as a supernova, or perhaps quietly implodes into a black hole, it will have already spent its final centuries throwing off those spectacular shells of gas and dust. That material is not just pretty, it is fertile. It is the raw stuff of future worlds. Every speck of carbon, every grain of silicon, every atom of iron that WR124 ejects into the interstellar medium is a potential building block for a new planet. And on some of those planets, if the conditions are right, there might be oceans. There might be atmospheres. There might be the complex chemistry that, given enough time and enough luck, leads to life. WR124 is dying so that something else might live. Its beauty is coincidental, a byproduct of violence and gravity and radiation. But that does not make it any less awe-inspiring. We are watching the universe prepare the ground for the next generation of worlds. And we are lucky enough to be here to see it. And here is the part that should genuinely stop you in your tracks. Here is the part that makes this whole endeavour worth it. We, a species that evolved on a wet rock orbiting a mediocre yellow dwarf, have managed to understand this. We have built a machine, a telescope named after a man who dreamed of rockets, and we have pointed it at a dying star that is 15,000 light-years away. 15,000 years. That means the light we are seeing left WR124 at a time when the last ice age was just beginning to recede on Earth, when humans were still hunting mammoths with stone tools, when the very concept of civilization was barely a flicker in the distant future. And yet, here we are, sitting in our living rooms, watching the ghost of a star because we built a mirror that is 21 feet wide, and a camera that can count individual photons. That is not just impressive, that is extraordinary. That is matter studying itself. That is the universe through us, turning its gaze inward and trying to figure out how it works. Carl Sagan said it best, we are a way for the cosmos to know itself. And right now, with the James Webb Space Telescope, the cosmos is doing a very good job. There is a common misconception that the more we discover, the more mysterious the universe becomes. People like to say that science strips away the wonder, that it reduces the night sky to a collection of boring facts. Nothing could be further from the truth. What Webb is showing us, what it has shown us with WR124, is that the universe is not becoming more mysterious. It is becoming more comprehensible, and there is a profound beauty in comprehension. When you look at that image of the Wolf-Rayet star, you are not looking at a random smear of light. You are looking at a process you can understand. You are looking at the life cycle of matter itself. You are seeing the blueprint for how every planet, every moon, every asteroid, and every living thing came to be. That does not diminish the awe. It amplifies it. Knowing that the earth beneath your feet is made of star ash does not make it less precious. It makes it sacred. It means you are walking on the remains of ancient suns. It means every breath you take contains atoms that were once inside a star that died billions of years ago. That is not a mystery. That is a revelation. And that brings us to the impossible discovery. What we thought was impossible is not only possible, it is essential. We used to think that the death of massive stars was a messy, chaotic, sterile process. We thought that the heavy elements that make life possible were scattered randomly, almost as an afterthought. We thought that stars like WR124 were rare curiosities, interesting but not central to the story. Webb has shattered that assumption. It has shown us that these dying stars are not exceptions, they are the norm. They are the factories. They are the engines that drive the chemical evolution of the universe. The impossible discovery is that the very things we thought were cosmic accidents, the violent deaths of the most massive stars, are actually the most important events for creating the conditions necessary for life. Without them, there would be no carbon, no oxygen, no silicon, no iron, no planets, no oceans. No you, no me. The impossible is not just possible. It is the reason we are here to talk about it. So let us pull back and look at the big picture for a moment. Let us put WR124 in its proper context. This star is emblematic of everything the James Webb Space Telescope was built to do. It is a symbol of transformation. It is a symbol of the golden age of astrophysics we have just entered. For decades, we looked at the universe through a narrow window. We saw the visible light, the radio waves, the X-rays. But we were blind to the infrared. We were blind to the earliest stars, the first galaxies, the hidden nurseries where planets are born. Webb has opened that window, and what we have seen has already rewritten the textbooks. The universe is stranger than we imagined. It is richer. It is more violent and more beautiful and more interconnected. WR124 is just one star among billions, but it is a perfect example of what Webb can do. It can take a distant dying sun and turn it into a lesson about our own origins. It can take a ghost and show us the face of our own past. We are only beginning to understand what the universe has been building all along. Think about that sentence for a second. It is not just a poetic closing line. It is a statement of fact. The universe has been building things for 13.8 billion years. It built galaxies. It built stars. It built planets. It built life. It built consciousness. And we, at this tiny sliver of cosmic time, have finally developed the tools to see the blueprint. We are like archaeologists who have just discovered that the entire planet is a single, massive artifact. Every star is a clue, every nebula is a chapter, every dying Wolf-Rayet star is a page in the story of how we came to be, and we have only read the first few paragraphs. There is a tendency to look at the vastness of space and feel small, insignificant, overwhelmed. But that is the wrong reaction. The correct reaction, the one that honours the work of the scientists and engineers who built Webb, the one that honours the sacrifices of the stars themselves, is gratitude. We are lucky to live in this moment. We are lucky to have a telescope that can see 15,000 light years into the darkness and bring back an image that changes how we think about our own existence. We are lucky to be the generation that finally connects the dots between the death of a star and the birth of a flower. So the next time you look up at the night sky, remember WR124. Remember that somewhere out there, a star is dying, it is shedding its skin. It is scattering its guts across the cosmos, and it is doing so with the same inevitability that the sun will rise tomorrow. That star is not just a pinprick of light. It is a promise that the universe will not stop, that the cycle will continue, that new worlds will be born from the ashes of old ones. And maybe, just maybe, on one of those worlds, a creature will evolve that will look up at the sky with the same wonder we feel today. And they will wonder where they came from, and the answer will be the same. They came from the stars, they came from the violence, they came from the impossible. We are only beginning to understand what the universe has been building all along. But to truly grasp the weight of that statement, we must first understand how profoundly wrong we have been about the timeline itself. Before Webb, we looked at the early universe through a fogged window. The Hubble Deep Field gave us glimpses of galaxies as they were billions of years ago. But it was like trying to read a book by candlelight from across a library. We could see the shelves. We could see that there were books. But the words were blurred. We assumed that the first stars and galaxies formed slowly, gradually, over hundreds of millions of years. We assumed that the universe needed time to cool down, to settle, to gather itself after the inferno of the Big Bang. We assumed that complexity was a luxury that came later. Webb has shattered those assumptions with the force of a supernova. It has peered back to within a few 100 million years of the beginning, and what it has found is chaos. It has found fully formed galaxies where there should only have been wisps of gas. It has found supermassive black holes already gorging themselves on matter when the universe was still an infant. It has found stars that must have formed in ways we cannot yet explain, in environments so dense and so violent that our models of stellar birth simply break down. The universe did not take its time. It was in a hurry. It was forging complexity from the moment it had the raw materials to do so. And that changes everything. It means that the processes we see today, the cycle of star birth and star death, the recycling of matter, the seeding of planets, were not late additions to the cosmic story. They were the opening chapters. They were the very first things that happened once the universe cooled enough for atoms to exist. And this brings us back to WR124 with a new level of respect. Because if the early universe was in a hurry, then stars like WR124, the massive, short-lived, violent ones, were the workhorses of that era. They were the ones that did the heavy lifting. A star like our Sun, a modest yellow dwarf, will live for 10 billion years. It will burn steadily, quietly, changing very little over the course of its long life. It will die gently, puffing off a planetary nebula, leaving behind a white dwarf that will cool for trillions of years. That is a beautiful, peaceful end. But it is not productive, not in the way that matters for creating the heavy elements. A star like our Sun will never fuse elements beyond carbon and oxygen. It will never create the silicon that makes the Earth's crust. It will never create the iron that makes our blood red. It will never create the gold in a wedding ring or the uranium in a nuclear reactor. Those elements require violence. They require the intense pressure and temperature of a star, at least 8 times more massive than our Sun. They require a Wolf-Rayet star. They require a supernova. So when we look at WR124, We are not just looking at a dying star. We are looking at the engine of cosmic enrichment. We are looking at the reason why the Earth has a solid surface, why it has an atmosphere, why it has oceans. Every single atom heavier than helium in your body was forged in a star just like this one, or in the supernova that will eventually end its life. You are literally made of the exploded remains of ancient massive stars. Your left hand might contain atoms from one supernova and your right hand from another. You are a walking, talking, thinking patchwork of stellar corpses. And that is not morbid. That is magnificent. It means that death is not an ending. It is a transformation. It is the universe's way of turning one thing into another, of taking the ashes of the old and building the new. And there is a deeper lesson here, one that applies not just to stars but to ourselves. We are finite. Every human life is a brief candle in an infinite darkness. We are born, we burn brightly for a moment, and then we are gone. But what we leave behind matters. The star WR-124 has been burning for maybe a few million years. Compared to the age of the universe, that is a blink. But in that brief blink, it has created elements that will persist for billions of years. Those elements will become part of new stars, new planets, new life. The star itself will be forgotten. Its name will be lost to the cosmic noise. But its legacy will endure, and the same is true for us. We are not here forever. But the things we create, the knowledge we discover, the art we make, the kindness we show, those things can outlast us. They become part of the fabric of reality. They ripple outward through time and space, touching things we will never see. And this is where the James Webb Space Telescope becomes more than a machine. It becomes a symbol of that legacy. It is the culmination of thousands of years of human curiosity, of trial and error, of genius and failure. It is the result of 100,000 people working for decades, pushing the boundaries of what is possible, refusing to accept the limits of the known world. It is a mirror made of 18 gold-plated segments, a sunshield the size of a tennis court, a camera that can detect the heat of a single photon. It is the most complex and expensive scientific instrument ever built, and it is sitting 1,000,000 miles from Earth, staring into the past, sending us messages from the dawn of time. That is not just technology, that is poetry. That is the human spirit reaching out across the void and saying, "We are here, we are small, but we are not insignificant. We are trying to understand." And what we are understanding is that the universe is not a cold, empty, meaningless place. It is a factory. It is a garden. It is a forge. It is constantly creating, constantly destroying, constantly recycling. It is alive in the only way a collection of physical laws and energy can be alive. It is a system, and we are part of that system, not outside it, not above it, not separate from it. We are the part that has become aware of itself. We are the part that looks at a dying star 15,000 light years away and weeps at its beauty. We are the part that builds telescopes and writes poems and falls in love and wonders what happens after we die. We are the universe experiencing itself. And so the story continues. It continues with every new image Webb sends back. It continues with every new discovery about the early universe, about exoplanet atmospheres, about the life cycle of stars. It continues with every child who looks up at the night sky and asks, "What is that?" It continues with every scientist who spends a lifetime trying to answer that question. It continues with every death and every birth, every ending and every beginning. The cycle does not stop. It cannot stop. It is the nature of the universe to change, to evolve, to grow more complex, and we are riding that wave. We are part of that process. We are not observers, we are participants. WR-124 will die, its light will fade, its gas will disperse, but its atoms will live on. They will become part of a new star system. They will become part of a planet. They might become part of a life form that looks back at the sky and wonders. And in that moment, the star will have fulfilled its purpose. It will have contributed to the one thing that matters more than anything else. The continuation of awareness, the persistence of wonder, the endless, beautiful, impossible drive to understand. We are only beginning to understand what the universe has been building all along. But we are building it too. Every time we ask a question, Every time we push the boundaries of knowledge, every time we refuse to accept the easy answer, we are adding to the cosmic story. We are becoming part of the legacy of every star that ever lived. And that is a responsibility we should carry with humility. Because we are not the masters of the universe. We are its children, we are its voice, we are its eyes. And with the James Webb Space Telescope, we are finally learning to see clearly. And what we see is a universe that is not done with us yet. It has more to show us, more to teach us, more to reveal, and we will be there, watching, learning, growing until the very end. Because that is what it means to be alive. That is what it means to be stardust that has woken up and started asking questions. And the answers, when they come, will be worth the wait. If this journey through the cosmos left you in awe, there is so much more waiting. Subscribe to This Is Space for deeper explorations of the universe, where every story takes you further into the unknown. Hit that bell so you never miss a discovery, because the universe never stops surprising us. Share this video with someone who needs reminding that we are all made of star stuff. Every atom in your body was forged in the heart of a star, just like the one we explored today. It is a humbling thought. We are not just observers of the cosmos. We are part of it. As always, keep looking up, keep wondering, keep asking those big questions. The answers are out there, written in the light of distant stars, waiting for us to find them. The James Webb Space Telescope has only just begun peeling back the layers, and the next revelation might change everything. Stay curious, stay hungry for knowledge. Remember, the universe is not done with us yet.